morning and welcome to the fourth day. Don and I, when we submitted this, we originally used the word standards and then plopped this presentation on the website and we went, oops, we used the word standards in our presentation. So I just changed it to guidelines. We don't have standards, we're just presenting a way that the ammonia refrigeration industry is headed and the way they train their operators. It's a lot of hands-on training. And this is kind of a talk we give at our national conference we've given it on the management track that we have to end users. We changed it up a little bit, but it's something that we have given at our conference because we feel it's a good message and helps end users. So it's geared really, would you say, more towards how an end user would set up their training program with the intent that it's something we are sharing now with the regulatory industry and what's out there and the resources that they have to use to train their operators with in an industry that's largely on the job training, but there are programs out there, there's materials out there, and there's a way to certify operators. So we want to share those with you. We're going to kind of go through why train operators, how to train them, what the resources are that you can use, and then the different aspects of why training is important, basically prevention and integrity. Trained operators know how to maintain the integrity of their systems and hence prevent releases just by doing their maintenance. We're going to kind of go through in general, specific training suggestions, where to get the information, general overview of ammonia refrigeration, and then we're going to kind of toggle into something that we think is an important aspect of an operator's daily job, which is the daily rounds, and why that's an important, and you'll see through this intro why the daily rounds is important. And anyone that was with me on Monday knows the daily rounds is, I'm making that an integral part of the PSM program, because the daily rounds, the operator checking everything every day, or in some cases they have people do shift rounds, is very important in avoiding deviations. That's the key for refrigeration industry, to avoid deviations to normal operating conditions, which is, we see it in process safety information and we see it in the operating procedures, how to comply with steps to avoid deviations. So, oh, you know what's missing? Our little pointer thing.
Is the remote mouse available?
The remote mouse didn't show up.
Uh-oh.
Whoops, I forgot to check that. But anyway, I can toggle as either one of us goes. So the training program, it's important because a large number of the incidents are due to human error and mechanical integrity issues. Someone goes to fix something because it's failing and they don't have their PPE on, or they didn't isolate properly. So those are really the purpose of a good training program. Emergency shutdown. Training is key to emergency shutdown. Anyone that listened to Gary Smith, which was Monday afternoon, muscle memory, preparedness, just knowing what to do when the chaos starts. So the purpose of someone's training program, these are the key elements here, preventing incidents, maintaining the integrity of the system, and being prepared for an emergency. Knowledge for an operator's power. In the event of an emergency, the muscle memory keeps chaos at bay. So what's required? Well, this is where the regulation has sort of stumped a lot of end users. It's 4 points, 4 bullets. You need to have some kind of initial training. You need to have a refresher training at least every 3 years. You have to have some kind of certification and test to ensure competency. And OSHA, PSM, and the RMP and the CalARP, these are written that way so that we can cover lots of industries. You don't want to tell a particular industry how to train their people when it might be different in a different industry. So, but at the same time, that vagueness sometimes stumbles the end user, like, well, what do you want for initial training? Yeah, I talked to the guy. So that's kind of where an end user needs to zero in and figure out what works in their program and what works for their industry. They need to come up with a plan of attack. So we talked about three main components, which is the initial refresher, documentation, record keeping, transfer of knowledge. The feds only have the three components. California has added the certification piece. And if you dig down into CalARP really deep, it gets to 2755.4 says you need to train people prior to making a change. So there's training that has to happen all the time before you make a change, on some kind of periodic basis initially, and you need to document it. So the end user has to come up with a plan of attack. They need to understand the benefits of training personnel. They need to understand what is certification. The skill or capacity should be duly recognized and documented. And as an operator, the benefit of certifying yourself is to prove that you are qualified to do the job. And it kind of gives you another level of confidence to be able to handle the emergencies, to be able to go into, say, the vice president of operations and say, we need this because. So being able to give the operator the tools to better understand their system gives them the power to go to the powers that be to get the money he needs to keep the system, to maintain the integrity. So that's kind of what we're gearing up towards, is giving the operator the power that they need to run their system effectively. The Ammonia Refrigeration Training Guideline is a document that was put together by International Institute of Ammonia Refrigeration, the Institute of Ammonia Refrigerated Warehouses, and RETA, the Refrigerating Engineers and Technicians Association. They got together and developed a guideline to help let people have a way of what do we need to do, what should we be training on, and give end users something to latch onto.
This was a project that started in, believe it or not, 1992 in Chicago at the RETA headquarters. We brought together people from industry. We brought the other associations together to start talking about, number one, do we need this? Well, the obvious answer was yes, but that was hard to elicit from this group of managers because they didn't know what they were agreeing to and what they needed. And it had to take shape. In 2002, the Industrial Refrigeration Consortium had a meeting, brought together the stakeholders. It was at the University of Wisconsin, and that's when they started to really engage in it. They put together a group of people from all the different stakeholders and started working on this. From 2002, it took until 2008 when this actually hit the streets. When you join RETA, and I encourage you all to join RETA, this is one of the first things you get as a member benefit is here's what an industry consensus document says about the training and skill competencies that an industrial refrigeration plant operator should have. You're all getting one today. Let's see. Let me jump into what I understand the certification requirements are. And I'm going to start with the Injury and Illness Prevention Program because when that was developed in 1991, it has a certification component in it that as you train your people, not just your refrigeration operators, but as you train your people, you are to document when they were trained, who trained them, what materials were used, and a level of competency. And that process of that documentation is a form of certification. One of the components of the requirement, and I see that thread goes down through other regulations all the way into process safety management and risk management program and CalARP, is an understanding of an overview of the process. And with the RETA certification, the entry-level certification addresses and completely satisfies that component. A person who holds the CARO RETA certification has demonstrated that they understand the overview of the process. They know what it does, they know what the pieces are, They know where the hazards are. They have comprehension of limits, et cetera. Good overview of the process. So if somebody presents to you, I got a trained operator and it's a CARO, that component is very well satisfied with that third-party certification. The other certification is what happens on site. And we really stress to the management that they need to understand, don't stop with just the RETA certification, because what happens on site has to also be certified. Going all the way back to the Injury and Illness Prevention Program, you have to train the people that they know what they're doing. And you could even go back to SARA Title III, that you need to have people who can respond to a leak. And responding to a leak is more than going and stopping it. You know, it's recognizing it and being able to use the resources available to communicate, and if they got the button to push or whatever. So the employer is on the hook for that certification. So there's third-party certifications, and then there's the on-site certification. Both are needed to fully complete the suite of certifications for the personnel.
How do the safety days fit into that certification program?
Wonderfully. The certificate of the safety days are meeting the going to the feds, the 1910-1200 HAZCOM. The safety days, some people thought, I'll use my 8 hours of going to the safety day and that'll satisfy my HAZWOPER, emergency response 8-hour refresher. And we say, no, that is not covered here because we're not doing the skill part and whatever. You are getting the HAZCOM part. The HAZCOM is, going back to double IPP, is an important component of the training. And again, supporting the personnel at the facility with their right to know and their needs to know. So the safety day helps reinforce that. And as you go from one safety day to the next, it's always building. When you come to Salinas this year in May, we are stealing from the RETA National Conference. There's going to be 5 different workstations set up for people to actually put the wrenches in their hands and do the task, adjustments, oil draining, and so on, line breaking. So in the afternoon, all the guys that are motorheads will be out doing a series of exercises, and the other track will be the emergency response track and the management track. So, so you take these opportunities, and then as the owner-manager, I have to decide how does this apply to my situation, and then be ready to defend it. But come on up to Salinas in May, May 26th, I think it is. Back to you.
Okay, thanks. And we're going to circle back to more certification and safety day stuff as well. But the safety days are a great tool that RETA chapters have used to provide some personal development hours and awareness training and hot topic type training to their members. And it's been a great tool. And ASTI has kind of helped some of the chapters that maybe didn't know how to jumpstart a safety day across the country actually jumpstart a safety day. So it's been kind of a neat process the last couple of years to see a lot of our we have 41 42 chapters, and probably half of them now are doing safety days, and the other half probably started in the last couple of years. So it's kind of exciting. Question.
I just hope you go on and when you can't make your hat on that.
No.
Right.
No. But it helps with.
Your training dossier for you yourself is a compilation of training and gathering information and knowledge from here and there and there and there, and that becomes your training portfolio. So yeah, the safety day is a piece of a portfolio. If the management is lazy and say, this is it, Rebecca's going to come and say, well, wait a minute. Does anybody know where the button is here to shut the thing off? And then she'll say, you need to spend a little more effort in this too. Yeah. And what does management want? Give me the button. I just want a button. But great point. Thank you.
Okay, so in planning a facility, when they're kind of planning their training program, the plan of attack needs to include what are you going to ask your operator to do? What are going to be their roles and responsibilities? Some facilities use a contractor. Some facilities have and all they do is daily rounds. Some facilities have a full-on maintenance team, and they can tear apart a compressor and climb inside and replace the coalescer. So it varies, and a facility needs to sit down and figure out what are we going to be asking these different operators to do? What are their roles and responsibilities? How will we understand that the operator understands what his roles and responsibilities are? What skill or talent is needed to do the tasks? Like changing out a coalescer filter, you're going to be going, in some cases, reaching inside. Well, there's confined space entry, lockout, tag out, working on a roof, fall protection. So the training program for refrigeration jumps outside of really even just handling the system. It also includes what safety issues and safe work practices are necessary to do the task safely. Understanding the ammonia system. Are there benefits of not training? Where do you find the training materials? What training method is to be used? These are all things the end user needs to think through, and then they need to document the training. Basically, the role of an operator is to safely start and stop the refrigeration system for either routine purposes or for emergency reasons. Even if you use a contractor that comes in and does the maintenance, you need to have an operator that understands this function. They need to be able to safely isolate and pump down any portion of the system for maintenance or emergency actions. In some cases, facilities use a contractor. Well, then they need to make sure the contractors people are trained to do this. An operator needs to correctly and consistently record system conditions on the log sheet. They also need to understand what they mean. It's one thing to go down and write down a bunch of numbers, but they need to understand what that means. If our system's running too high, is the pressure too low, are the levels off, are we purging too much? So then these are things, and this is something we're going to go into a lot more detail in a little later, but the operator needs to understand the relationship of these numbers he's writing down. Needs to understand the trends. If he sees, pressure trending up or something trending down, needs to see that before it becomes a problem. Steps to avoid deviations to normal operating conditions. Safely drain oil from compressors and oil pots. Whether or not it's a contractor or someone on site, oil draining is going to have to happen, so somebody who is at the facility needs to understand this task. To know and understand what the refrigerant is doing at any point in the system. This is key for troubleshooting. If you have a log sheet and you see a trend that correlates to understanding what's going on, are you at liquid, are you at vapor, are you saturated or not saturated, is it, where are we in the system? Because the ammonia is changing as it goes through its cycle. That Don will explain over here at some point. To understand the broader issues of the vessels, operating levels, velocities, temperatures, the nameplate. Can't tell you how many nameplates get painted over when you're trying to collect data. They get insulated over. We need to understand our relief valves. Question? Mm-hmm. Uh-huh. So the question, I'll let you answer, but the question is, I have an old piece of equipment, the nameplates pretty much can't read it, but you have the UNA form.
Okay.
What do we do?
Yeah, you can apply to the national board to get a duplicate nameplate, and they need that UNA information, et cetera, and they'll contact the manufacturer and authorize a new data plate to be made. That data plate needs to be installed by a certified individual. With the equipment that I'm responsible for, I'm replacing a lot of nameplates. And the cost of replacing a nameplate, my most expensive one, has been about half the price of the vessel, just because of where it was and the cost of getting that certified individual out there. It was about $2,000, I believe. But the point is there is a process, and you start with the national board and download their form for requesting a duplicate or a replacement nameplate. Yeah.
What's certified individual? I mean, I know you are, but.
Well, oh, yeah, certified, actually certified to do that kind of work on the vessel. So it would come from a certified vessel shop. For example, in Fresno, there's Ransom Manufacturing. They're a certified vessel shop. They build most of the vessels you see going down the highway and the propane trucks, the 10-wheeler trucks. A lot of those vessels are built by them. So they dispatch their certified people to affix the nameplate. And it's also witnessed by a representative from CalOSHA when it's installed in our state here. So yeah, certified to do what they're doing. My certification as an operator wouldn't allow me to legally put that nameplate on. However, as the certified operator doing maintenance, if my nameplate's coming off, I do have the authority to get new pop rivets and pop rivet my original plate in place. But if it's a duplicate, the role of that certified individual is to confirm that that data plate's going on the right vessel. And they have the understanding of determining that, yeah, this is the right vessel. We're not doing anything we shouldn't be. Yes?
If you're taking data plates off from old and replacing them with new ones, what happens to the old that have to be destroyed by a certified?
I haven't had that situation. I don't know. I don't know if the installer would take it and fold it and crinkle it and destroy it or whatever. I never considered that.
Run into a situation where you've got an older tank system, the manufacturer is no longer around, but you need a data plate. How does that?
The way it's worked out for me is, because the manufacturer is no longer in business, the national board gives that certified shop the information, and they create a data plate with the information, and then it's affixed onto the vessel. One of the things that we're doing now is when we buy a vessel that's going to be insulated, it comes with two data plates. It has the one that's on the shell and gets covered up, but it's also got one on the structural leg. And when we first asked the vendors to do this about 8 years ago, they pushed back. They said, "Oh, you can't do that, you can't do that." And we explained to them the situation and the need, and they agreed, okay, we'll do this. So when you go out and you see in some vessels, you might find the data plate is now on the leg where it's dry and clean and gets to stay there. That's a trend that's happening now because data plates, they put them on with the cheapest of rivets and they're there and then suddenly they're not. And so putting it where you don't have to corrupt the integrity of the insulation to confirm it's there. So if you see that out in the field, it's a new trend.
So can we laminate like a U1 form or something and put it on the side, tag it on a something like that?
I guess you might if you care to, but if your document, if your file system has the UNA in it, you can bring it to the vessel. I guess it all depends on the situation of the inspection or the review. We're wising up and doing a lot of digital file storage and actually building complete equipment-specific document folders, digitally. And so the UNAs are available there. Works great, for being able to transmit the information without, every time you take something out of the file cabinet, you risk putting it back in the wrong spot. or it doesn't come back. So having the digital works out really nice.
They can also back engineer. Ransom actually has done that, and back engineer if there's no U1A and no plate, if for a really old, pre-1950-ish something vessel, they'll actually go in and they x-ray and they can back engineer the whole thing. It's expensive, but it can be done.
Yeah.
I've seen them do it.
As a businessman, you have to look at the practical options.
New vessel.
Replacement, new vessel versus the reverse engineering and certification. It all depends. It all depends.
Okay. The role of the operator. Learning objectives listed in this guideline represent the consensus of a representative ammonia refrigeration industry group that included consultants, contractors, educators, and end users. So this is kind of going to go into what's in this document on the next few slides. It actually lists out how you could classify suggestions for classifying an operator, entry level, operational level, and a technical level, with learning objectives for each of these levels, all in the document. Entry level would be someone who observes system operations, records the pertinent information from the daily rounds, take control actions only under direct supervision of a supervisor or an operator level personnel. Operational level, say the next step up, successfully perform at the entry level, start and stop the equipment, adjust controls, actuate valves, perform routine system maintenance, assist in training the entry-level personnel, and perform system troubleshooting. So this is another level that you could have in your shop. You have entry-level people, maybe there's a certain period of time you give them, your operations group. The technical level, this could be a supervisory type person, make decisions regarding operating strategies and set points and limits. We need to change, we got a different product coming in, so we need a different temperature, how long it's going to take to get the room, how hot's the product coming in, what do we need to do, optimize system operations for improved cost and reliability, energy efficiency, hot topic, how are we going to make sure our cold storage rooms are running most efficient as possible, best use of the power supply, run the engine room at night versus high peak power times, schedule and perform major repairs and rebuilds, recommend system upgrades and improvement. This is the person that's going to say, the compressor needs to be replaced because blah, blah, blah. We need another compressor because we're not keeping up with demand. We need another condenser because we're not rejecting enough heat. Perform system inspections and mechanical integrity checks. Someone who's doing a little bit more than your daily rounds. Participate extensively in the process safety management program. This would be the person who understands what's in the volumes and how to make sure we do our management of change and the pre-startup safety reviews and how we handle contractors. Perform complex troubleshooting, oversee or inspect system construction or installation activities. If they're doing an add-on, the technical level person would be interfacing with the general who's doing the installation. Supervise the operational entry-level operators, coordinate shutdowns and pump downs, administer preventative and predictive maintenance systems. If there's a work order system, make sure everything's getting done in a timely manner. Do we want to hand out the book?
Yeah, it's time to get up and walk.
Okay. So this book it's well written, it's to the point, it has some of the information I already went through and then a little more detail, some background. It's a good guideline for end users and it's straightforward and to the point.
And it was developed using the protocols of developing an ANSI standard. And it is still a guideline. What is happening today is the International Institute of Ammonia Refrigeration are developing standards. And they will publish those as standards for plant operators. That work is being done now. It's through the public review. Actually, it's in the development. Public review will help and will happen here before long. Once it's a standard, it'll be easier to understand. This is what the industry says, and to apply it, as the end user. Everybody has their own understanding of what they need to do in terms of training their people and what's required. You, as people that go to different sites, see probably a wide variety of training effort and measurements. So the standard is coming. In ammonia refrigeration is about 110 to 120 years in existence since the process was first invented. So it's nice to now have a standard coming.
So the operator needs to understand what's going on in all portions of the system, like what's happening. We got lots of different components: vessels, compressors, condensers, evaporators. So we're going to kind of go through here and oh, not yet. Not the pictures aren't yet. And we're going to talk about and show some pictures of all the different components. We have heat absorbing devices. That's the evaporators are taking heat out of a room. Jacketed tanks are taking heat out of a product. Energy adding devices, compressors that are helping kind of drive the ammonia through the cycle. Heat rejecting devices, that's where the heat that came from the room is now going out into the atmosphere. We have temporary storage where the ammonia might sit for a little bit as it's moving through this process, and then of course the piping, which is the transportation system. There's safety systems that the operator needs to understand. We need to understand what these safety systems are about, refrigerant characteristics, what it's doing in different parts of the process, chemical exposure prevention, what are the flammability issues with this refrigerant, consequences of upset, and just even the cost of operating the system.
Okay, heat absorbing units. We call them evaporators. And the reason they're called evaporators is we bring in liquid ammonia or liquid refrigerant into the tube circuits that's inside the casing, and we draw the air or whatever it is we're cooling, because it could be a water chiller and you're having water film come down over the heat exchange surface. But the point is the purpose there is to draw heat energy out of whatever the media is that's being cooled and transport that heat energy away. So the evaporator brings in, it has liquid ammonia brought to it. The process of the heat absorption causes a reaction. That's a strong word, but it does affect the refrigerant. The purpose of the refrigerant is to actually evaporate. So heat energy causes the evaporation by the addition of the heat energy. The heat is borne out by the vapor. It leaves the system and goes back toward the compressors. So this is a air cooling unit. This is a unit that's cooling water. Water comes down over this plate, and inside the plate is the circuits where the refrigerant flows. This is a unit that is a batch cooler of some sort that maybe 30,000 pounds of warm lettuce just came in out of the field and is put in it. Actually, probably cauliflower. And the refrigeration system is provided there. This is out of doors. Traditional facilities, seems like most everything is indoors as far as process and all. If you go to a freezer plant, you've got the traditional engine room, condenser up on the roof, everything is inside the building. Fresh produce, majority of things are actually out of doors, something like this. It's a component of our modern life that people don't see, how the food comes out of the field and the routing that it has to go through in order to be delivered to you at the plate. But systems that are outside are very common in certain parts of the Southwest and in the on the East Coast as well. Go ahead and click. So, refrigeration is a cycle. And has anybody in here been through some of the courses that maybe were made available, PSIG or others, RETA classes, etc.? Okay, good, good. I might call on you. Huh? Is that right?
Yeah.
Make your own refrigerant?
No, I just was, last night I was a little confused. I just wanted to just add some examples. I had some person who ended up taking it apart, but it's not perfect this time. It's quite pretty, but it just explains the whole process. Wow. Apart, install in place. It's pretty educational.
Comment was
Everything's on
YouTube
YouTube.
as a resource for illustration or for understanding a process. Good, I'm glad you did that. So I'm just going to very briefly wave my hands in the air and explain the cycle. There's more coming about that. You know, the whole purpose of a refrigeration system is to maintain a temperature. In some area, we want the temperature to be cold. And in other areas, we would want it to be warm. And so to achieve that, we build a closed loop system. Closed loop meaning that the fluid that's inside the system, the ammonia today, stays inside the system. But the heat energy, because of the way God made it, will transport through a solid. So the heat energy can come onto the surface of the heat exchanger, the evaporator. Whoops, back up. I'm sorry, Lee. The heat energy will go into here, but the barrier, the physical barrier, doesn't stop the heat energy. It can go right on through the walls and find the colder substance, the ammonia. The difference of temperature drives the activity. The greater the difference, the faster it's driven. The heat energy enters, the fluid responds. If I come up and put a warm blower on you, you will feel the effect of the warmth coming onto you, and your body will warm up. The body of the liquid that's in the evaporator is going to warm up, but because we maintain the pressure of the evaporator, that warming up, instead of it just getting warmer, causes a change of state, changing from liquid into a gas. The reason it does it is the result of that heat energy coming in. The gas has to go somewhere. If we don't let the gas out, then the pressure will rise until the heat energy no longer has a differential, and then that's where it'll be. If we allow that to happen, we're not getting the job done in refrigeration. So we have to have something to send the gas to without heat that has just entered into the system. That's the purpose of the compressor. The compressor accepts the gas that's being pushed to it by the heat source and adds more energy to it. It's taking the volume that is pushed into the compressor and reducing that volume. And the consequence of reducing the volume is the pressure goes up and the temperature goes up. It expels out, looking for the next differential point of the system. And the next differential point is where we want to reject that heat energy to a place where it does no harm, basically the atmosphere. And that's done with a device called the condenser. The condenser is a gadget that maintains I'll call it the environment. It'll maintain the conditions where the condition of the gas that's coming to it, it's hotter, and over here we maintain a cooler situation, and that heat energy now that's being transported inside the pipes will come to this condenser and find that, hey, it's cooler on the other side, and it'll go through the walls of the heat exchanger, taking the heat energy out of the gas and rejecting it to the atmosphere. And the response of that gas is to now condense into a liquid. That liquid then leaves the condenser and it's ready to go back to the evaporator. Most industrial refrigeration systems will have what we call the high pressure receiver. High pressure receivers vary in sizes based on the needs of the facility, the quantity of refrigerant that's there. So traditionally you will see a high pressure receiver accepting liquid from the condensers. It's a wide spot in the pipe. You know, we have, what, 5 pints of blood in our bodies, basically, and it's always circulating. Refrigeration system has X amount of refrigerant in it, and it's circulating, but how much circulates at any given time is dependent on the heat load that is there. At night, the heat load is low. In the afternoon, especially in fresh produce, which is my forte, in the afternoon, the heat load is high, the rate of movement, circulation is higher. But the point is just like us, you know, we keep the blood inside us. Refrigeration systems, you keep the refrigerant in the system, it's moving around. Pressure differential drives the physical movement. Heat temperature differential drives the direction in to evaporate and then out to condense. In between the condenser, or after, let's say that after the receiver and in front of the evaporator, there's a pinch point, a place for expansion, because we've got a high pressure on one side and we have a lower pressure on the other, and you need to have something that is the separating device, and we call that the point of expansion. In our systems, we have expansion points that are fixed, and so the rate of flow through them depends on the pressure differential driving, and we have some that respond, and they respond in order to maintain a steady flow based on the needs. So overview of the refrigeration system, it's closed loop. It's about differential temperature, and it's about differential pressures to make the system function. Actually, I'll be, later on, we'll be looking at this graphic here. This is an excerpt from the RITA course book number 2, that explains the system, what I just did now, for 2 different types of refrigerant feed to the evaporator. But as a basic system, there's evaporation, there's compression, there's condensation, and there's a point of expansion, just 4 components of a cycle. Wow.
I followed through with you.
Did you?
Yeah, we got, and then when
but
you
then I
said
stood in
expansion,
front of it. I'm sorry.
when you hit expansion valve, I went to the low side. We question.
Yeah, the question is, it is a closed loop system. At any point do you have to add? Yes. Yes. Pipes are not 100% impervious. And ammonia, or any fluid, eventually it can work its way through the molecules. In a refrigeration system, because we do maintenance, there will be opening of the system. There will be breakdown of the refrigerant in that, you know, it's, for ammonia, it's made up of hydrogen and nitrogen. At some point in its life, it can dissociate. make what we call non-condensable gases that is a bane in our life. If you have gases that won't condense in your system, they add to the total pressure, and that's problematic. So yes, there are times when you need to add. The lucky guys are those that are they're built, they're not adding new equipment, new processes, or taking processes away, and they establish this is my operating charge, and they can work with that charge for quite some time. And then there will come a point in time where they realize, well, we need to add X amount of pounds or gallons to get back to where we want to be. The rate of adding, it all depends on the facility.
That could be, I mean, that time frame could be 20 years, could be 30 years. I mean, an ammonia refrigeration system is tighter than your cars. Most good ammonia refrigeration systems, well maintained, are tighter than your car's air conditioning.
Yes, thank you. And that's why I hesitate to put a number on it. Some processing plants will actually transport some of their equipment to another processing plant, so they're opening and closing, and it's a more difficult job tracking your inventory level. That's why the vessels are sometimes sized the way they are, because if you take away part of the process to be used in another location, well, you don't take the refrigerant with it, you leave it in your system, and so wintertime levels might run a little bit higher in a vessel compared to summertime because of where you're using it. I'm sorry? Great. Let me see if I can restate the question. One part of it was how often should you do maintenance? And what was the other part? Yeah. Okay. How often? How often is a decision that we make based on, number one, what does the manufacturer recommend? We have that as a guidance, and I say that's a guidance because a manufacturer gives you the maintenance requirements not to make the device last longer, but to get through the warranty period. See, the manufacturer wants to get through the warranty period, but he wants you to buy another one real soon. so they give you maintenance recommendations. Some facilities will just follow. Okay, every year we do this, and there's good reason for that because the condition can be that this machine really doesn't need this now, but because of the annual cycle of the facility, if they're seasonal. I can't wait for 3 more months till that I get the full life of my oil because I'll be in processing. We'll change it now. So the facility needs to establish this is our program. And you follow, again, you can use the manufacturer's guidance. Compressor manufacturers will say, change the oil and only use ours. And I appreciate your... But as the end user and the responsible person, I can say we will use this oil and we will use oil analysis to tell us that it's now time to change the oil. Oil can last a whole lot longer than the guidebook would say if you are actually indeed measuring it and change your filters. I'm amazed at how some people with their vehicles will change the filters twice before they change the oil. but they're into it, you know, and that's important to them. They see that. So getting the most out of the equipment is you know, what the maintenance is all about. When we do open up, for example, Lee mentioned opening up and changing the coalescers. Throw up the screw compressor. You're going to love this because in true training fashion, we're going to tell you what we're going to tell you, and then we'll tell you, and then we're going to tell you what we told you. So by the time that we finish later this morning, there'll be a lot of deja vu here, but bear with us. In the compressor package, this is what we call a screw compressor. There's a horizontal tank here, and this horizontal tank, its purpose is to take the lubricating oil out of the gas stream and leave it in the tank so the gas stream can go onto the condenser without the oil. They're not 100% efficient. Oil does get out into the system, and that's why we have to drain oil. But these compressors have an opening at the end, which is a manway, which allows us to access just inside. There's a filter. This coalescing filter is an element that can be about this long, and there might be two of them stacked end to end, and about so big around, and there might be an array of 3 or 4 of these. Right about here, there's a barrier, a bulkhead. And on this side here, this is the side that takes the gas stream from the compressor, and it's moving. You know, this particular size unit might be shoving out 1,200 cubic feet per minute into this dead end, and that's by design. And it comes to the barrier, and then it has to squeeze itself through these coalescing filters. And the coalescing filters wring out the oil, and it drops to the bottom here, and then there's a system to bring the oil back into the storage side of this separator. Well, we have to maintain those coalescers. They are filters, and so they can clog up over time. And if we don't catch the fact that they're clogging up, something's going to give. You know, the pleating will open, and then all of a sudden they're not doing their job of coalescing, and we're sending a lot of oil out into the system. Remember those log sheets? Mm-hmm. If all of a sudden we're adding a lot of oil, you know, that's a clue to us, hey, you better check our coalescer, something's not right. So now we open it up, air comes in, there is some amount of loss of the refrigerant. Refrigerant vapor doesn't take up a lot of space. A pound of, a cubic foot of vapor at condensing pressure might have, you know what, I'm not going to give the numbers. I have to look it up. There are tables. But the point is liquid, there's more mass in liquid in a cubic foot than there is in gas. And so we lose some. Don't ask me how much I lose when I do a coalescer change. I would be guessing, and I don't want to guess in writing. But the point is it's very little. There you go. Thank you. It's very little. Yes.
I think the question, though, is relative to the hazmat inventory and the hazmat material business plan. Any type of HVAC system, compressor system, anything that has this constant thing is going to have there's going to be a designated charge. You go up to an HVAC unit on the roof of a grocery store, and you look at it, it's going to say, this unit is charged 334 pounds of R134A. If you sucked every bit out of that thing, you might get 326 pounds, you might get 202 pounds, whatever. When it stops working efficiently, you add refrigeration. That's leak rates. Everything has a leak rate.
Mm-hmm.
Stuff's going to leak. Same with the refrigeration system. We add refrigerant when we get to the point that the system is not operating optimally. Some people have more closed systems. They don't do so much maintenance. They don't open it up. You can't estimate. There's no way of figuring out what that inventory is without pumping everything out of it, putting it into a container, weighing it,
Yeah.
So most of the inventories you'll see are conservative. We think we have more than we actually have.
That's true, and thank you for bringing me back to the point. On our inventories for the refrigeration systems, it's an art and science to actually come up on a running system, say what's really in here. And what we do to do that is we look for the liquid, because the gas component is, by comparison, just a very small percentage of what the total is. So we go looking for the liquid and determine how much is here. And in a pump down like that, and bringing it back to a vessel where you can get a level on it and run the numbers. The thing about the inventory is that we do want to declare what is here. We're obliged, of course, and of course that magic number. Well, there's a couple of magic numbers, but 10,000 pounds takes you from one program requirement to another. The risk management, the federal risk management program, the federal process safety management program, and another magic number is 500 pounds in California, because that is the threshold for CalARP. Of course, we do realize that it's all discretionary. You have the discretion that, if we got a system that maybe has only 300 pounds, but you deem it enough of a concern, you might ask us to do a CalARP. Or you might even say, well, yeah, you've got more than 500 pounds, but I don't deem you to be that great of concern. You don't have to do a CalARP. The inventory is a thing to be watched. An engineer, somebody will determine, here's what the initial charge was. We put, case in point, a location that I'm involved in. We built the system in 2003. Last year, we put in 1,000 pounds. And in between the time, we operated. We added a condenser, and that condenser is why we had to add the 1,000 pounds to put things back to the balance we wanted. So you can, as the gentleman said, I'm going to get you the hand mic, I think. So, anyhow, when you ask somebody, show me how you manage your inventory, ask them that. Don't ask them what is your inventory, because they're going to break out into a sweat. And because they're going to, oh my God, how many times did we do this and that, and what are you looking for? But ask them, how do you manage your inventory?
So I didn't realize, so you change the oil on these?
Yes.
I didn't.
Yes. Oil changing. Well, we'll get to that too. So, yeah.
Oh, and there's,
Part of an RMP though, and a refrigeration system, you need to know your maximum
Yes.
inventory, intended inventory. Because of pressure and temperature, they're very related in an ammonia system. In order to get the appropriate cooling temperatures of whatever it is you're cooling, that is affected by how much ammonia you have in the system in various locations. So you do need to have an overall pretty good idea of what your chemical inventory is, simply because if you have less than 500, theoretically, then you don't have to do an RMP. If you are over, if you're different programs, and then if you hit the 10,000 or more, then you
Yeah.
have to report to SET. So it is up to the facility to really come up with that, and then as the COOP inspector to verify where you are in that process.
Right, and Linnea's reinforcing, the reason for the maximum intended inventory. And there's a lot of buzz going on out there in the LinkedIn world right now about how do you determine that. I see some silliness out there on how some people are stating it. But you have to have enough to do the job. And how much you need in any given point of the system depends on its conditions at the time. So part of our challenge as the engineers that operate or provide the service is, okay, how much is enough and how much will be too much? and then you find that sweet spot, and that's how we establish from one facility to the next how much we actually need here. Then it's that matter of, okay, here's my number. Plant that you visit in the Santa Maria area, 24,000 pounds in this plant, is enough. 19,000 pounds is not enough at certain times of the year. So that's what we need to do, is we need to find, okay, what is our maximum intended? The way we're simplistic. We need what we need. The question might be restated, when is it too much? And if it's too much, you have elevation of pressures and so on that you don't want to have to live with. It's not that it gets to be unsafe, it gets to be unprofitable because we're pushing against a pressure load that we don't need to inflict on ourselves. But yeah, maximum intended inventory is one of those questions that we respond to in industry, like, do you still kick your dog in the morning? How do you answer that? It's because it is different for every site. What I hope you will understand is it is different for every site, and your question is, how do you know? How do you know that you don't have too much? Thanks, Lene.
Yep.
So, I'm not kind of sure, but does the PSM or the ARP program, does it require that you need to have inventory done every year? You need to update your inventory?
Actually, the Tier 2 reporting, that's where we're doing it in this state. The business plan, yes. So we do affirm our inventory quantities, and that is a requirement. Beg your pardon? How's it going? The question is how is CERS doing? My consultant is having a nervous breakdown because he has a lot of kittens in the box to keep in the box when he works for our company. We didn't really, well, everybody knows Lee and what she does. I work for a company called Western Pre-Cooling Systems, and we're involved in the post-harvest cooling of fresh fruit and vegetables. And our equipment is portable. More than half of our equipment is down in the Yuma area, Imperial Valley area right now, working to provide good, safe salad to the world. So we have all these locations where we have responsibilities, and our consultant, I've been working with him since since SARA Title III, the Tier 2 programs. He's been a part of our operational family since the late 1980s. He is working on the CERS so that he can go to each of those facility managers and get them established as the person who's putting in the numbers and the certifications. And he is having a breakdown because the timeline and the perceived complexity of it. When Kirsten went through it the other day, it didn't seem to be that hard, but to be honest, I'm letting Ray do his job, and he's working with the managers. So they're getting there. I think the more that he does it, the more comfortable he'll get. That's how it's going. If the CERS program will give us the opportunity to maintain the information on a more timely basis so that it is useful to the regulatory world, to the response world, is part of the driving force for having CERS so that the responders have more timely information. Is that one of the goals? That'll be great. From my side, as the phone numbers change of who's in charge, who's the contact person, having that to go to as a portal to give the information, and it propagates out to all the proper areas. If that's how this network will work, then I like that.
Good.
Is it time to walk?
Just tying a bow on the inventory thing. All the facilities are slightly different. You have vacuum, facilities that run in a vacuum, facilities that don't, food processing versus box storage, oil draining issues depending on what type of compressors you have. And one of the things actually came from an end user. Well, first, IAR suggests that facilities maintain a delivery log, and then this came from an end user who wanted to say, because maximum intent inventory shows up in your PSI, it shows up in your worst case release, it shows up on your EPA submittal, it shows up on your tier 2, it shows up on your RM plan that you submit to the CUPA. When you do get a delivery, why did you get the delivery? And we actually put on the log, he asked us to put, does this change our maximum intended inventory, yes or no? And then 5 years later, when the guy's gone and CUPA comes in and says, well, why did you get this delivery of 1,000 pounds? Well, it's on the log because we added a condenser, and the condenser required, the size of the condenser, it's 1,000 pounds of ammonia to make it run properly. Yes, it changed our maximum intended inventory. Yes, we fixed all the things. Did our management change? So that's kind of a tool that you could suggest if people are sweating when you ask the question, like, hey, when you get a delivery, just write down why. What happened in the last 5 years? And it probably didn't change your maximum intended inventory, because like Don said, they're usually an engineered number that makes your system run efficiently. And if you have too much, it won't work. Too little, it won't work.
Good. The heat rejecting device, this is that box that you see on the roof, or you might see outside of the building. The heat energy is coming from the compressors into here, and this is where that cooler environment is. Now, it's not that cool. Well, it might be 80, 85 degrees in there, but compared to the temperature of the gas that's coming to it, it is cooler, and so the heat energy will move from where it's hotter to where it's cooler. Thank the Lord that's the way he made it, and you can always count on that. And so the heat energy actually leaves in that steam plume that you see from these devices. When you look, when you're driving down the highway later tonight and you go past a facility and you see that steam plume coming out, well, that heat energy you see the evidence of, it came from inside, or whatever it's doing inside. Next. Again, going down through the cycle, here's an example of one of those white spots in the pipe where the refrigerant will fall into this, and the level can change throughout the day. Again, the reason the level changes, it's because of what's going on out there at the evaporator side. If nothing ever changed with the evaporator, if the need rate was always constant, you wouldn't need very much of a vessel. But in refrigeration systems, well, even in your refrigerator at the house, the tubing that comes down from that little radiator grid that's on the back of the refrigerator to its pinch point, that's a wide spot where the refrigerant can languish until it needs to be pushed into and through the evaporator. So anyhow, these devices, they're ASME rated vessels, different pressures, traditionally at least 250 psi G. 300 is becoming more and more common. They are protected with relief valves, etc. And again, the level changes. There's also low pressure temporary storage devices that are used to maintain a level in order to satisfy the need of a pump, or to protect when liquid does come back to the compressors. Compressors don't like to compress liquid. It's problematic. So you put an intercept device here so that it can capture the liquid so that only the gas goes on. Take a close look at this. We're going to have our final exam based on this one. Go ahead and click. Refrigeration transport. We have pumps that can, in some systems, will pump cold liquid out into the cold storage space to deliver that liquid to the evaporator. The return flow is a function of gravity and the push that comes from the evaporating, because the pressure is trying to rise where that heat went in, and that is what drives back toward the engine room. And then you've got the compressors that's creating a lower pressure on its inlet in order to accept the flow. We got refrigeration components, valves, strainers. Valves and strainers are there to serve a purpose, wide range of purposes, to control a pressure, to control a flow. Hand valves that provide positive shutoff so that we may do maintenance and or under times of crisis we can find the valve that will, if we close this one, what's happening down there will be affected. It'll be controlled from I call it the arterial valve, closer to, away from the problem, but if you close this one, you get a result over there. One of the things that we try to impart on first responders and on site folks is to identify these arterial valves. Is everybody in here an EMT or EMT trained? You know, if I have a real bad gash right here, you might come and put a compress on me right here, but I bet you some of you will come up here and find where you can pinch off the flow so that I'm not bleeding so bad. Consider that.
That cut the whole heart off, like some of these responders want to come in and say, where's the shutdown valve?
Oh, please don't do that.
So if you're bleeding on your arm, you're not going to shut your heart off.
Right.
I mean, it's the same thing.
Exactly.
Never thought
Right,
of that.
right. Yeah, if it all comes out, it all comes out. But the point is sometimes, see, this is where it gets fun in the legal side. You know, you have to have so many hours of training. The offensive action to bringing about a control of a release, right? Well, if I got a valve that I can access without going into harm's way, am I doing something offensive or not? That's one of our dilemmas in industry is how much can we do with the training and the personal protective equipment that we have that can bring about a positive situation without having to go and get it right in our face. Because in the early days of the emergency response regulations, it was always looked at the perspective of like golf, you know, you got to play it where it lies. No. We can come over here and affect it, or like in golf, you know, you do that. And foot wedge, yes. So consider that. Again, when you are coming out to the facilities to support them. That's the way I see it. When Rebecca comes out, she's there to support me. Ask them, hey, have you guys identified a couple of your key valves that you might be able to use? Don't say, where's the button or where's the box? You know, again, oh my God. But, because that will give you an idea of their understanding of the system. They might even have it formalized in their emergency action plan, which is the ultimate goal. You know, if you do the initial inquiry, hey, do you have this? Well, not. Well, why don't you think about it and maybe put it here in your emergency action plan. Train on it. So valves, they're there for a purpose. They do wonderful things. Again, our goal in a refrigeration system is to maintain a temperature. To do that, we have to control flow and we have to control pressure. And so the valving does that for us without me having to be at each device and pinching down the flow or opening things in order to get the work that we want. There's insulation systems. I was in Dallas last week attending a conference, and one of the presentations was corrosion, not corrosion under the insulation, but what's being seen as corrosion under the aluminum jacket. I didn't realize that was a problem, but it is a problem. I think it's probably more of a problem down in Texas and the Gulf states. The actual aluminum jacket, the reverse siding of it is is having, they find a corrosion problem there, and the jacket will deteriorate. So this presentation is how to understand it and what might be done about it. Our concern more with the cold storage is the corrosion coming down and to the in attacking the pipe in the first place. I'm sure that's your primary concern as an inspector. Anybody here ever do any kind of hunting? I grew up in Minnesota, and so this is California. We don't hunt in California. Okay, you don't admit it. I grew up in Minnesota, and in my teens I did hunt. I hunted partridge, and the first year or two of hunting was difficult and not very fruitful because I was hunting all the time and just looking for that bird. And suddenly I realized, the birds are more where the clover is. So I wasn't hunting birds, I was hunting clover, because where the clover is, I might find the bird. When you're looking at issues with with possible corrosion on insulation systems, one of the places where you find the bird, or where the clover is at the bottom of these vertical runs. The water can enter up here and it'll come down and pool. When you go out to inspect, please don't make me strip all of my insulation off, because you really want to see what's under it. And I'm reluctant to even take the hole saw and bore a hole so that you can take a look. But there are some places where you do want to look, and occasionally, and it's at these corners here where it can pool and gather. So that's one location where you might ask to let's have a look-see now and again. Piping that changes temperature cyclically, such as the line that comes from the evaporator when we defrost. It'll be cold, and then it's pushing a warm fluid through it. So you have these temperature changes throughout the day of this line. That is the line that more often needs attention compared to the big line that's next to it that hardly ever changes its condition. So look for where the clover is so you can find the bird. You had a question. If the piping's buried underground. Wow. When you put the pipe underground, you can put a pipe that is perforated, like one of these perforated plastic pipes that runs in the same section with the piping that's underground. And if it leaks from underground, this perforated pipe would pick up the odor, and it comes up to the surface and gives you a place to check now and again. I've seen that used. That doesn't always work so well. It's a great idea, because, okay, if I'm leaking underground and I got this perf pipe and it's going to come up, so we know, depending on how it's installed, if that underground piping is allowed to get very cold, now you're wicking water from the atmosphere down in there, and you're delivering water to it to cause a problem. The underground piping, your indicator would be, why am I having to recharge here, but I'm not driving anybody out of the neighborhood with a leak? So an underground pipe would be a place to go look. I guess if your records are really good, you might be able to take a post hole digger or whatever, and very carefully go close and see if there's any odors coming up from the adjacent ground, where it would the ammonia would absorb into the earth. But I've seen, like I say, these these vent lines that give you a place to check, but you got to be careful about how you put them in.
Don, no, way in the back.
That's one way. And I just want to also just agriculture, you check it right in the soil, and then you get ammonia and so on, so you always check the pH.
Yeah, the statement was, you know, in ag, we purposely inject liquid into the soil for application of fertilizer. And so the suggestion is actually drop a sample of the soil and check for pH, get a control reading over here, and get close to where the pipeline is. It's just that as you're going down, depending on how close you're trying to get, you want to be careful that when you get to that location where these pipes are, they may be all enveloped in a vapor retarder, and you go in there with your gadget and puncture that, you've introduced a problem. There's a question back here.
Actually, there is non-destructive testing that you can do on part that can measure up to 100 feet from the test point, like any current type of device that they can take this test.
Uh-huh.
So at a spot above the ground, you can have their device and they can measure 100 feet of that.
Really?
It's available. Didn't expect that, but
Wow. That's a gadget that you insert and it has to travel inside the pipe, or is it?
it has to be outside of the pipe. And
Uh-huh.
then basically it measures use currents.
Sweet. Because I was envisioning a kind of like a medical procedure there for a moment, but
That's how they test bridges also, because you can't tear the bridge apart with steel.
uh-huh. So the non-destructive testing using eddy current apparatus. Did I see another hand a moment ago? Lee, are we anywhere on point? Go ahead.
Yep, most of these pictures have been pictures of good and well-maintained systems. But are there any benefits of not training? We have some pictures of failures, mechanical integrity failures. That costs money. That's not a benefit.
Your motor's not supposed to have a right angle on its output shaft. This was a bearing and lubrication problem that really went bad. There was no ammonia release associated with this, but this is a 500 horse motor and that shaft was turning at 3,500 RPM when it did ultimately fail. No injuries, no whatever inconvenience to that user, because 500 horsepower is providing a lot of refrigeration for you, and then suddenly you're down for the next 7 or 8 hours while you scramble to find a 500 horse motor, get it installed, get it aligned, get the rotation right, and get yourself back online. They had a business interruption for part of their throughput, and well, these motors aren't cheap. What's right with this picture? Remember what I was saying about where the water comes to and all that? I'm trying to give you clues so that as you go out in the field, you can focus your hunting. You don't have to be like I was my first 2 years of hunting partridge. You know, look for the clover. What they're doing here is this is where they're removing oil from that part of the system. And so they got a hand valve and a collection point and another hand valve. And Lee, can you tell that is a self-closing valve there?
I'm thinking it's not.
Okay. In fact, that might even be associated with another line. Point is, does the operator know what this does, how to do it, what is the personal protective equipment, and is there a better way? We promote the use of self-closing vented valves for the oil draining. We call them dead man valves. Purpose being that when you open it, if you let go because you drop dead, the valve will close. And One of the more dangerous tasks in maintaining and operating a system is the oil removal. There are some systems provide vessels to collect the oil to, so that you can limit the amount that can come out of the system if something goes wrong. Others don't have, this is part of the live circulating system. Having the dead man valve as the permissive is a great tool. You've got the primary valve where your operator is throttling the rate of the oil removal, and the dead man is the permissive. And if it suddenly is no longer dispensing oil, it's spit of liquid, all he's got to do is, oh my God, and it's terminated. He can close the valve, open the other valve, and his task is done. In 1994, there was a oil draining tragedy in Pennsylvania. Some sort of a setup that was like this, and these poor fellows were on a scissor lift to make it even more difficult, because where they had to go to do this job, they did not have a self-closing valve to protect them. There was an operator receiving training from the more experienced fella. The more experienced fellow was the assistant fire chief in the fire brigade in that community. Back then, we weren't as well informed as operators and owners about the existence of the permissive device, and it's been that way since they put the plant in the 1940s. We always did that there. Well, there are sometimes devices that can be used to improve the situation. In Oxnard, back in after we learned of that accident, we ordered 100 of those self-closing valves. I ordered them on Friday. On Monday morning, a facility was draining oil and had a runaway oil situation. And anybody here know Steve Elkington? He was the AA agent from City Fire back then. He says, well, Don, what are we going to do to prevent this from happening again? I said, Steve, you're not going to believe this. I just ordered 100 of these things. So he was happy to see that we were proactive, and it was unfortunate. Again, no injury, business disruption. We took resources from the city, because we had to respond. So if somebody had a fire or an accident, they were tied up in this other situation. These self-closing valves are really good. When you ask your facility that you're supporting, do you have these things? And they say, yes, we do. Okay, great. Are they vented? And the reason you're asking them, are they vented? One of the dangers of trapped refrigerant is if you trap liquid and it gets warm, it's going to swell. I'm not going to use the word expand, because expansion means something else to us in refrigeration, but it's going to swell. The density of the fluid changes with its temperature. In a ball valve, you've got a cross section that is basically the size of the pipe, and then when you turn that like that, you've trapped what was in that into here, and now it's got nowhere to go. The appropriate ball valves for oil draining have a hole drilled through one side that goes back to the system, so that whatever you trap in here, when it warms up, can make its way back to the system. So if your facility is proactive, we got these self-closing valves, ask them if they know that they are vented, so that you don't have this potential breakdown because of the warming up. Again, we've got an example of a hydrostatic damage that can happen.
That might be oh no.
Oh yeah, there's benefit in not training my operator. This is what the inside of your reciprocating compressor can look like if it takes on a liquid and doesn't get its lubrication. This one was costly. It didn't cause a leak, but you know, not training is problematic. Remember that device, the condenser, that's to reject the heat energy? The more you impede that transfer of heat, the higher the pressure is going to be. The higher the pressure, the more you have to pay in power to reject that heat, because of it's a difference of your inlet pressure of your compressor and its discharge. And if you turn your heat exchange surfaces into a coral reef, that's a good insulating jacket. This bundle here is not a coral reef. The irony of this is in the same box. So, again, I'm a practical engineer. What's going on here? Well, this one's not crudded up. Why? It wasn't seeing water. If it doesn't see the water, it's not doing a lot of work. This one is scaled up. It saw the water, but we didn't control the quality of that water with respect to its dissolved solids. And so as the water evaporates from the surface, it's leaving the minerals behind. And part of the art of operating a condenser is maintaining a good chemical water dissolved solid balance in the water. So this one wasn't addressed the way it should. So this condenser wasn't giving us the performance it needed to give us what we needed. Good heat rejection at the lowest price. This user was paying a lot of money for not training his operator to know what to look for and to do.
And just before the break, one more benefit of not training, and before we get into, after the break, we'll come back and talk about where to find training materials and what certification that RETA offers, as well as daily rounds. It's not always about the money.
This is injury to Scott Silva. Happened 10 years ago. He was doing some maintenance, and he was surprised by a very small burst of liquid ammonia that came out of a portion of the pipe that was in a vacuum. If you ever been to some of the ASTI, the ASTI trainings, you might have seen the video of Scott's explaining what he was doing, and his chagrin for the fact that he didn't put, goggles on, or might have just put on his air purifying respirator. But for what he was doing, he was not anticipating that a burst of liquid spatter and a cloud would come back out of a pipe that was in a 29-inch vacuum on him, but it did happen. This is the day after. So he tells a very compelling story, because he was on a scissor lift too, and couldn't see, couldn't breathe, didn't know if he should jump. It was really something to hear his story about a month after the accident. He came to the RETA chapter meeting and said, "I'd like to talk about what happened to me." Very compelling. Scott's face is completely healed up. It's back to his baby skin. And his eyes, no damage there. But what he experienced when he was in the ER, they did put a medication in his eye, and that's when the pain really, really started. So they had been doing flushing, but when they put the medicine in, it seemed to trap whatever ammonia was still trying to come out with the flushing, and that was a lot of agony for him there. Bear that in mind if you're involved in an emergency response, about the value of the first aid and decontamination for ammonia exposure is the one same thing, and that's fresh water, moving fresh water. For Scott, when they put the medicine in, that's when it really started to hurt him.
All right, so we talked a lot about the pieces of equipment, what happens at each piece of equipment. So we'll circle back and get back on our, I'm an end user and I'm trying to develop my training program. I've kind of defined what I want my operators to do. So there's lots of places. Of course, we're going to push Rita a little bit right now. Refrigerating Engineers and Technicians Association is a good place to go for training materials, for operators to network with each other during chapter meetings and learn from each other's experiences. Opens the doors of opportunity for learning about ammonia refrigeration from a very basic level to a full understanding of system operation. We have course books. What's kind of neat about Rita is the chapter meetings at the local level, and it's a place where people kind of, some of the experiences that, questions and answers that have been given today. Hey, this happened at my facility and don't want it to happen again. And like Don mentioned, Scott showing up at the Rita meeting a month after his injury, like, hey guys, this is what I was doing and this is what happened. So it's a networking of refrigeration operators. Chapter-based organization similar to ASHRAE. There's local meetings. Our mission is to enhance the professional development of the industrial refrigeration operator.
How much time classes
Hold that thought. Go through where your references are. There's references through IIR. They have an extensive library with manuals, standards, bulletins, and videos that people can grab from to learn about ammonia refrigeration. They have a nice poster on oil draining. Site-specific training for PSM compliance. That's made up of standard operating procedures, participating in process hazard analysis studies, participating in audits. These are all things that you can use. They're training materials. Your PSM document is a training material. Training opportunities at Rita chapter meetings, regional events such as the safety days. These are all opportunities that an end user can say, well, yeah, I'm going to do such and such initial training, and my refresher training is going to require that the operator attends one safety day within 3 years or attends certain number of chapter meetings and so on.
Okay.
Also, on-the-job training, reviewing operating procedures at the end user's facility to comply with PSM. Independent study, that could be a lot of time. Small group studies. Some of the Rita chapters do book classes and they hold those, and our chapter did a book one, IR book one, and they met once a month for about they met twice a month for about 2 hours, and it probably took them 7 months to get through book one. So if you kind of compress that into time to answer the hours.
To go through Industrial Refrigeration Course Book 1 is about a 40-hour commitment. I know that personally. It took me 24 hours to read each word and punctuation point to my wife because the Rita management in 2003 changed the book without authorization. And they really messed it up. And so 24 hours to read the book without comprehension, about 40 hours to read the book and comprehend. Yeah, read Industrial Refrigeration Course Book number 1. There's a series of course books, 1, 2, 3, 4, basic electricity, etc. As a member, you get discount.
Confirmed transfer of knowledge. So we've developed our roles and responsibilities. We've found where we can get training. We've kind of defined what we want our operators to do and where they're going to get this training. And now we need to make sure that they understood the training. So the employer needs to take the responsibility to test individuals being trained. Test scares people in the end user world. When you say test, they freak out. So, we try to, you can do demonstration, you can do written tests, you can do interviews. One facility I went to, the chief engineer for his annual SOP review, which is a requirement, takes his SOPs and he puts in mistakes and then hands them out to his operators to go certify. And if they don't come back with the mistake fixed, then he knows they kind of failed a secret test. But the guy doesn't know he's being tested, so he's not panicking. It's not a sit down at a desk. But it is a way of testing. So there's a variety of ways that a facility can issue a test without making it sit down and fill in the little circles on, with your number 2 pencil like we had to do in school. How can an employer, the end user, who is well versed in developing customers, managing books, scheduling shifts, develop a test for such a specialty? So this is where the end user kind of gets stuck, but how do I test? Well, one example, the chief engineer hands out SOPs with mistakes. But continuing on with the transfer of knowledge, there's 2 primary categories, core knowledge and specific study. So do they have a basic understanding of ammonia refrigeration? That's their core knowledge. And then do they understand your system? If it's a box warehouse, it's operated differently than a food processing system. If it's 2-stage versus single stage, do they have screw compressors versus recip compressors? So all of those, while core knowledge gives you the overview, specific study is for your particular system, and they do need to understand that. Basically, for your daily rounds person, the RITA has set up 2 certifications, and the first one's called Certified Assistant Refrigeration Operator, or CARO. And this CARO is IR Book 1 plus IR Book 4, which is safety.
Yes.
And, it is a test, and you do have to go to a specific test center, and, it's on a computer now. You don't have to use your number 2 pencil anymore. But it is a way to determine transfer of knowledge for your entry-level operator. Another thought, as a consultant, I've taken it so that when I go to my clients, I can show them that I understand how their system operates from a general, 20,000 foot level. And one theory is that operators or regulators take this exam.
Can you talk about that? Because I'm interested in that. A little bit about the course.
Well, there are courses, and there's self-study. It basically functions off of Book 1 and Book 4. Book 1's a lot of introduction to ammonia refrigeration, and Book 4 is all safety. So it's all stuff you guys know.
Well, maybe not.
But it's kind of customized.
Yeah. So the books are designed to be self-study. Each chapter has a end of chapter exam. The key is in the back of the book. The reference to the question is in the key, so that if you're testing yourself as you go along, you can go back and reinforce from where the information comes from. They're available, through the RITA website. They're written for, well, we think it's 8th grade level understanding. It's written for the practical person, as we call it. So it's easy, hopefully it's easy to understand the concepts as it comes off the page. Illustrations such as these to help explain the points. So you can self-study. If the local RITA chapter happens to have the program going where they are studying as a small group on a periodic basis, see if you can get into that. There are training opportunities that happen in the state. For example, the Arts Academy, Michael Schreck and Corey will have 24 or 40-hour courses where they are studying, say, Book 1. And you can get into that opportunity. You would go to their website to see what's happening, what's scheduled. And there are training consultants that come in from out of state. Garden City Ammonia Program comes to Bakersfield kind of regularly and presents for a week or so. So look for those opportunities too. But it is designed so that you can sit at the kitchen table and read and understand. The group setting makes it more fun and applicable because the practical application stories from experienced people come into what's coming off the page. And so look for the opportunity. Rita also offers the course book, some of the course books in an online version, which is kind of the Reader's Digest or the Cliff Notes version of the book with the end of chapter test questions as part of it. And that's a subscription-based thing. So there's a number of ways to get to the information. But reta.com to see the publication order form is like step one after you join. Take the discount.
A number of years ago, several of us regulators had it's not something to be taken lightly. We do need to say that yes, it is a very difficult test. It's very difficult. And as I remember, it was a couple hours.
Yeah.
Somehow miraculously, we passed. But it was one of those tests where I walked out and I was on the edge.
Yeah.
It wasn't like, oh, yeah,
I,
we got to study.
I really appreciate his personal testimony there, because when you come to a facility and you see that the operator has that same credential, you have an appreciation for what that person, and that's why we want to encourage you all that do regulate and inspect, challenge your own understanding. Yeah. So here. Thank you. Linnea.
I went through the Garden City training and did 40 hours, lovely Bakersfield in August.
Oh, geez.
I was the only regulator, the only woman. It was a hard class, even for, the gentlemen in there who do it every day. They have a different perspective, we have a different perspective, but it really did help, and I'm gonna see if I can audit again this August. But the other application is with other CalARP facilities or general type engineering plant. There's a lot of flow diagrams, things like that, that maybe it's not for chlorine, but kind of the principles are there, and you might learn something from that that you can apply to different facilities as a regulator.
Mm-hmm.
So it really is it's a good understanding. It's a lot. And the Caro it's just a lot, but it's definitely worth it, because then, like when I meet with Don, he knows I know a little bit more than I did the day before because I went through this.
Yeah. And I really appreciate those that did take that exam and challenge that, because it gives me, like I say, a better appreciation for you. There was a horror story, no good deed goes unpunished. An individual took the test and was successful, and then went to a facility and wanted to see the expansion valve. So here's my expansion valve. And the line was iced downstream of the expansion valve, and the inspector wrote a violation because of this ice downstream of the expansion valve. The plant operator, he was quite harumphed over that, and he came to me squawking, and I said, well, okay, yes, it was a teachable moment. The person had the credentials for being an assistant. It was okay to have, you need to have the pressure differential, the temperature differential, and ice will form. That's a normal thing. But the person, just didn't quite have that concept down. But it was an enforcer, so like I say, this manager was kind of harumphed at the time. Information is, okay, information is good. Applied information is power. Yes. So there's opportunity. Gary.
Well, I guess my question would be is the ice formation. Was it a violation from ice formation, or was it so much ice formation you couldn't get to the platform?
That wasn't defined to me, but in that particular system, I don't think it was that situation. It was just a misunderstanding of what's supposed to happen at that part of the system.
How much does it cost?
The course price varies on who's delivering it. For example, what Mike and Corey teach. I think they have a regulator's discount, maybe. And again, the $110 book that gives you all the resources, but you don't have the benefit of being in a small group. It's available to you at $110 at member rate. You're welcome.
And one thing that was interesting is, back in 2002 is when you guys started the ANSI accreditation. Rita started.
It's when we committed to getting
to having this, and that's something we got to fix the slides because it's not emphasized on the slides. But the CARO and the CIRO tests are ANSI accredited, and what that means is it's a defendable transfer of knowledge exam. It's a defensible test, and to an end user, that's very important because the test questions are secured. We have a psychometrician, which is a new word that I learned when I got on certification committee, basically a test writer who manages our test questions, and he is constantly evaluating the performance of every question, the performance on how people, what answers they're picking. We evaluate, we go through this evaluation as a committee once a year to make sure the questions are performing properly as we expected. If there's bad questions or questions that are too easy or too hard, or so and ANSI looks at that every year and comes in and audits Rita to make sure that they're maintaining security, that there's a firewall between education and certification, because we have an education committee that writes these books. We can't be on both committees. We have separate committees, and we try not to have, we don't even have meetings together to keep the test questions secure and to maintain our ANSI accreditation. And a statistic that came out of all of this, our psychometrician is very much a numbers person, a lot of statistics, a lot of data. And what was fascinating is the CARO exam, people that take the 40-hour course or take a structured training and then take the exam have a very high pass rate. They pass the test.
Not all of them.
Not all of them, but the pass rate is higher for those that don't take any kind of preparatory course. The CIRO, which we're going to talk about, which is a certified industrial refrigeration operator, which requires 2 years of hands-on working in a system and is more about troubleshooting, the course doesn't really help. It doesn't make a difference whether you take the course or you don't take the course on whether or not you're going to pass, because it's more muscle memory, knowledge from being out and troubleshooting and learning, and so the course doesn't help as much as it helps with the CARO.
Yep.
Which was interesting.
Yeah. Click the slide.
I think this shows what's in.
What covers, yeah. And again, the people that do achieve their accreditation are presented a shoulder patch that they can put on their service jacket, and it is a badge of distinction. This is a registered trademark, or it's got a registration number. It's protected, and it is dispensed with each successful test taker. Some companies purchase them to put on everyday uniform because they are proud that they have their operators are certified. Go ahead.
The CIRO is a little different. This is more about an operator's skill, knowledge. This is more operations or technical level that we talked about from the Ammonia Refrigeration Training Guideline document.
Yeah, and the distinction between the two, because they're both time tests, 3 hours, a certain number of questions. The entry-level exam is testing you on your knowledge. The CIRO exam is testing you on your ability to use that knowledge. It's testing your skill for critical thinking and applying the clues and the data that's presented you in an exam question and resolving the correct response. And folks that aren't too keen on taking tests will reply, there's too many trick questions, meaning they couldn't figure it out from the 4 responses of what is the correct response, and that is by design. That's one of the most critical parts of writing a defendable test, is that you have one clear and concise correct answer and 3 that are close enough that somebody who's trying to figure it out on the fly will be steered off to the wrong thing. And that's what our psychometrician does for us. He says he's the resident psycho, and he's a kick. I never thought that in my whole life that I could work with a PhD on a technical exam and enjoy it. And once we got to know each other, he's a hoot.
How does it parallel to, I guess you might know, the PE exam, the
Yeah. Right. The question is, how does the RITA exam compare to delivery and content of the PE exam? I don't know about that specifically. But the exam, as Lee mentioned, is a controlled structure, controlled access, specific locations where the exam can be given. It's treated like national secrets, and the reason for that is it was a huge investment. Well over probably $400,000 by now in the last 10 years of doing this, is to give you, the judges, confidence that that test is indeed as up and up as it can be. And that's why we went to the highest authority we could find, which is the American National Standards Institute, to hold our program and feet to the fire so that we deliver the best measurement method for our member, our client, so to speak, and that you can have confidence in that. It's not come in, figure it out, and send it down. Yeah. Both. Yeah, as you achieve it. Yes. Sure. But you know what? Here's what I'm happy to say is happening. More and more of the end users, as they select a contractor, will say, you know what? I want the guy who comes. I want that, because they now have an awareness and an appreciation for that, what that emblem means.
I can bring up a point real quick. I brought up YouTube, and on that they had people taking apart like Walmart's air conditioners and sticking the condenser, coils into water and making something over nothing because they don't protect their own hands. And I'm thinking, okay, this is like Freon, and maybe it's not that dangerous, but then I hear these other classes, they're phasing out the CFCs. So are they ever going to have more and more humans pay hydrogen, which is very dangerous, do that kind of stuff? And do you perceive in the future that they might even have like little box units that's going to be hydrogen as refrigerant?
Oh, absolutely. Yes. And the question in the statement was about what was seen on YouTube of people taking apart a window shaker or whatever, and maybe putting the condenser into a pool of water to gain more effect, maybe, or whatever they were trying to accomplish. But at the end was, with the phase out of these man-made refrigerants and the hazards they bring with global warming and ozone depletion, what are the alternative refrigerants that are coming into play? And the natural refrigerants, the 5, are coming back into popularity. Ammonia is the, I don't know why he made it so, but it is the most efficient refrigerant in terms of its cost to compress and condense, the pressures that it operates at, how much heat is born in a pound of that ammonia. It is the most efficient, and it has like the 0 global warming potential. It just stinks, which is a good thing, actually, for early warning. Yes, propane. Propane has just about the very same temperature pressure characteristic as ammonia. So you're working in the ammonia equipment can indeed deal with propane. It scares the heck out of me. because it's not the propane that's in your barbecue. Propane in your barbecue has garlic oil or something in it to give you, well, refrigeration grade propane does not, because that stuff, that goo, will plate out into your evaporator and in your valves and gum them up. As a forklift mechanic in my developmental years, I had to rebuild the fuel systems on propane forklifts because this pickle oil would gum up the regulators and the carburetors. So the propane that's in a hydrocarbon refrigeration system does not have the warning oil to give you notice. Hydrocarbon refrigerants, okay, you won't be able to detect them with your natural senses. I am very comfortable with ammonia. I am scared to death of most anything else. Deja vu all over again? Yes. The comment about dry cleaning having perk, leaving petroleum product, now petroleum products coming back into popularity. You know, we have to do what we have to do. You know, the science community has determined some of the rate of change to our planet, you know, is affected by man-made processes. We have to change what we can to reduce that effect. So now, the popularity of ammonia. If we were in Europe, it would be common to see at the supermarket a refrigeration system that would be sending carbon dioxide out into the supermarket cases, absorbing the heat, bringing it back to a central point, and exchanging that heat to an ammonia system, which then rejects the heat into out into the environment. The first system like that in the United States was put into service at the Albertson store in Carpinteria a few months ago. It has less than 500 pounds of ammonia. It's got reciprocating compressors. It's got the compressors for the CO2 system. It's standard stuff in Europe. It's new to us. Rita is working with the Refrigeration Service Engineers Society, RSES. These are the group that are the boots on the floor, the rags and wrenches in the pocket like the Rita people are, but they work on supermarkets and rooftops and all that. And we're working with them to develop a safety bulletin and a guidance, because I am very concerned that a rooftop guy is going to be eventually working on that ammonia system and is not going to know what they need to know. And but this is the way of the future. Coca-Cola, Pepsi-Cola, putting CO2 refrigeration systems into the dispensing machines now. Not the fountain machines, but the bottled and canned. They're also got butane. They're using butane, and they're celebrating their green. Of course, they don't pay for the power that it takes to do that compression and heat rejection. So the cost of power of operating that thing and the collateral cost of the power generation, and that doesn't come out in the marketing piece about their green. But again, they're changing, getting rid of the HCFCs and the CFCs to the more natural refrigerants. Change is coming. What we want the industry to know, just like our collaborative effort with RSES, is get that information out there. Because when anybody has an ammonia leak, we all have an ammonia leak. And you can, how many of you just subscribe to the Google alerts for ammonia specific? Google has a function that you can subscribe. You say, you know, anytime there's a word ammonia in a news article or whatever, you know, send me that link. And so every day I see, I got ammonia in my fish tank, how do I deal with it? That's what happens a lot. And then, but you also see the news that there was a traffic accident and and a leak, or a cold storage had a leak. There was a Saturday or Sunday, I picked up the Google alert of the problem at Long Beach cold storage that happened over the weekend. So that is a free subscription that you can do that. It just brings you the information, but you can see the trends from that. Back to what's going to be at the supermarkets. Eventually, there will be people working on those that are encountering it for the first time. And what I know is going to happen is somebody's going to grab a brass plug or a brass gauge and put it in and leave it. And the incompatibility of ammonia to brass is going to, in a few days, dissolve that brass enough to where it's leaking, and then we have a big problem in the local area. Yes, it's a small quantity, but the odor doesn't take much to cause a real concern, even if it's not really doing harm. But causing a concern is also harmful.
So as you can see, the CERO is a much more extensive study that people have to go through. It's not just book 1 and 4, but we include book 2, which gets in more detail, electricity, and some control theory documentation as well. And again, like Don said, it's a lot about troubleshooting. There's a lot of screenshots of compressors and questions that ask you, what's wrong here? Or why is this not right? And you have to kind of sit and think about it and pick the best answer. There's other publications that you can use to study exam content, basically fundamentals and introduction concepts, 23%, refrigeration cycle, properties, tables. It doesn't have a percent number on there.
It's okay. Blow
Yeah.
through it.
Oh, here it is. There we go.
Yeah.
I thought there was a
Blow through
sheet
it.
with thing. Badge. There is a 2-year. You need to document that you've been working in the industry for 2 years before you're allowed to take this test as well.
Well, if you did operate and start and stop or maintain as a technician an industrial refrigeration system for at least 2 years and you're documentable in the past.
It's a really hard test.
Right, it is a prerequisite. Yeah.
Yeah.
The CARO exam is open to all. What I like to see sometimes is that we do make it available for a regulator, but we won't credential you as a CSIRO. But give you a chance to taste the test. But you know what? You can taste the test. We have a practice exam that's available online. Pay to play. It's $59, but we have the CARO exam and the CERO exam. 50 questions, and the questions are drawn from questions that rotated out of the active question pool, and or questions that would have been in the active pool. But you get a good sense for what's in the exam from taking this practice test, and that's open to all. Just need a credit card and a link to the internet. There's links from our website that can steer you there as you navigate through the links. So to get a taste of it, it'll cost you $59. But it does give you, again, a sense for the knowledge of those operators and their employers that demonstrate we have this. Actually, it is. Yeah, it is. It is well, for your CEUs, you'd have to negotiate that with your board. But taking that exam and all for the RITA examination, there is a 3-year renewal requirement, 24 professional development hours over those 3 years. If you flake out and don't do it, you have to take the test again. So renewal is becoming a very common thing now with the certified operators. They're finally getting it. It was a real culture change to go from, I passed my level A in 1991, why do I have to take a test again in 2007? And it's, well, guess what? Things have changed, and the credibility of the exam has changed since 91. 91 was a tough test. You were tested. But to be an ANSI accredited program, we had to tell all of our operators who had their credential that it still means something, but if you want to be in the program of the future, you have to take this test. And we broke that news to them in Portland, Oregon. The reaction looked like the assault on Frankenstein's castle. Yeah, those lumberjacks didn't take it well. But then somebody got up and explained it better than we did, how it sets them apart. And it's up to them. If you want to be set apart, you want opportunity, just do this. Now they are leading the way in testing and renewals.
So yeah, the renewal process is, we kind of kept it on a 3-year cycle, like the refresher training for PSM, and it's professional development hours are continuing education units, and we require 24 personal development hours over the 3 years. Safety days, RETA chapter meetings, the national conference, self-study, testing, all different things that can continue with the keep your certification.
Yeah. What's next?
Self-study, document it.
Blow through it. Good.
We went through that.
Did we say that we want you to join the association?
There's, it's time to stretch. Grab the Rita Breeze, and if you haven't already got, or if you aren't already getting a green copy of the Breeze, if you just go email agencies@rita.com, and you can get this document that we have up here front, you can come grab electronically.
Yeah, we'll put you into the special subscription database. You don't have to be a member to receive that. As a regulator, it's complimentary. We want you to know what we're telling the industry, and to make this available to you that way is the best way we know how. Thank you. So we want you to get up, get some movement again. Rita Breeze here.
I'm going to change.
Please take, and then take one of these as you go by.
And this is,
There.
does she call the man?
From your perspective, how many different elements of compliance and what we do are illustrated in this from 1963? Did you catch? It was an ammonia refrigeration system. They sheltered in place. They're going to call the fire department. It'll all go away once, contractor qualifications, training, lockout, tag out. I mean, we could spend an hour just dissecting this piece of entertainment and how it applies to us. But I wanted to share that with you because it conveys the message. When you show it to the manager, it's what's your value system? Aunt B wanted a bargain of beef. And then she had insufficient equipment. And then she had the problem and she brought in insufficient support. And she ends up with a new freezer. But point is how do you listen? How do you value things? So many good things just from that one clip. Being an operator. So what I want to do is we'll go through, what do we do here? And I'm going to actually give you an overview of the process, which will be about the third time you've heard it today, but that's not bad. The compressor orientation, pressure and temperature explained, and then we'll read it and we'll see it. And if we were at a facility, we would be doing it. So now put yourselves into here's your situation. I just hired you. We've gone through the interview process, and you're going to be my plant rounds person. You're working into my refrigeration staff, and you're going to be doing rounds. So this 11 by 17 that I gave you, it's going to be hard for you to read right now, but that's okay. We're going to follow some snippets from it. First of all, an overview of what we're doing here. Here's a facility that is actually an ammonia refrigeration facility in a land far, far away. And this facility cools strawberries. So at this facility, we have a building over here, which is where the refrigeration compressors and the condensers, you can just make out that these are condensers here. That's where we compress and reject the heat, and the liquid ammonia is conveyed via a pipeline back into this building here, where it's used to provide refrigeration for this part of the facility and right there. There's a second engine room right here on the south end of the facility that is providing refrigeration for most of the main building. The biggest part of the building is refrigerated with a nominal quantity of refrigerant, about 5,000 pounds. There's a third system here where there's a refrigeration compressor and condenser right here adjacent to the building that provides refrigeration for equipment that comes and goes on a seasonal basis. About 2,000 pounds there. And then the normal charge over here is, again, about 7,000 pounds. So no one system exceeds 10,000 pounds, but this facility chose that because they all have a thing in common. If a fire happened here, all three systems are active in the same general location, so they are treating the facility as a Program 3 CalARP RMP PSM facility, even though it could be argued, we got co-located separate systems, but a fire here will make a problem in all three locations, so we're doing RMP there. So what does it do? It's there to take in your strawberry that's just came from the field, and the only thing I think in the world that's more fragile or time sensitive than fresh strawberries is concrete that's in the transit truck from the batch plant to you. There's a short window of opportunity for the cement mixer to get it out of the cement mixer before it locks up in it. For strawberry, time critical from harvest. As soon as you separate it from its plant, it's dying, and you have to get it under refrigeration. And it's today it is the name of the game. Is how long does it take to get it from the field into refrigeration? And the customers, the Driscolls, the Nature Ripes, the Very Freshes, the Giants, that is a metric that they are measuring. They're measuring the field crew. How long does it take? Nobody's stopping for coffee on the way anymore coming from the field. And it's all part of the quality process. So we see traffic that comes through the facility here. The trucks come in from the field. They're offloaded in this general area. The product is brought in with forklifts. Forklifts are the acronym for them are PSU, pipe seeking units. Yes. It's Cooper, right? You got to have acronyms. PSU. There are evaporators that move a lot of air in hundreds, about 30,000 cubic feet per minute per fan to bring a lot of fresh air, cold air. I shouldn't say fresh because that implies it's coming from the outside, but we bring air across the product to rapidly bring the temperature down. So our job here is to maintain the temperature in that room, because if it's too cold, we freeze the berry, and that doesn't work for us. And if it's not cold enough, it doesn't get cold in the time that it takes, and we have quality issues. When the berries come off of the cooling units, they're brought over to this segment of the building for temporary storage. You know, they might be there for not even the full day. When the market gets glutted, they might be there for 3-4 days. My job is to make sure that the room temperature is right that whole time, again, so that quality at market is there. Drivers that come to pick up the product, this is where they back into the loading dock. Drivers are, they're an interesting breed of person. And the dispatch people, they have special skills for working with the drivers. All it takes is 2 trucks to get lost in this town to ball up all of the traffic in town because they're where they're not supposed to be. But at any rate, product comes in on a daily basis. It might start coming in about 8 o'clock in the morning. And it can continue until well into the afternoon or the evening. And our job here is to receive it, get it entered into the information system, get it cooled, get it over here, get it out on the right truck, and do it repeatedly day after day after day without any issues for the customer. As the refrigeration guy, you know, my job is to make sure that the environment, the air temperature is right there, and that my compressors can respond to the load as it comes. And now you're my rounds person, and you're going to help me see to that. Next slide. So we have what we've given you is a publication we call the Conference Chronicle. When you come to our conference, one of the things that you receive, I mean, we have conference for training, education, and we use a lot of different vehicles to do that. One of the things that we do is we slip this publication under your door in the hotel room. So every night there's somebody walking the floor at about 3 in the morning, a volunteer, delivering your newspaper. So you got the Conference Chronicle from this last conference we had in San Antonio, and it happens to be called Rounding Out the Rounds. And it's a description of the responsibilities of what a rounds person does, and that's why we're giving this to you now. So rounding out the rounds, let's go ahead, Lee, please. You know, again, an overview of the cycle. This is what we're doing here, and my responsibility with you as my new hire, you may be a Carroll individual, or maybe you're not. You might be somebody who's been with a company and you've done a great job in the production side, a good lift truck driver, you've got good work ethic, you have aptitude. I want to move you up. But you haven't had a chance to be to a course or whatever. So we'll do a review of what the basic refrigeration system is. You will find this in Read a Book 1 when you buy it. And it describes the function of the 4 components of the cycle, and also that there is a high pressure receiver. And right down here in the fine print it says the high pressure receiver is not a required component of a refrigeration cycle. But I already explained to you why it's there. Also, where you can't see it, we got our point of expansion here being a valve. We also have the compressor where we have low temperature, high volume gas coming to the compressor, and we have low volume, high temperature gas, high pressure gas leaving. On the low pressure side, cold side, that's called the low side of the system. So part of the slang when you go out to the facilities and they say, well, it's out there on the low side. Well, in your mind you can say, okay, that's after the point of expansion, but up to and entering the compressor. You can expect low pressure, low temperature activity there. And then you have the high side, the output of the compressor to the condenser where the heat is rejected, liquefaction happens there. The vessel that may be involved in the temporary storage as required throughout the day and back. And again, we just have a cycle where we're absorbing heat in here, transporting it, rejecting it there, and just continually reuse the refrigerant. The cycle is the same for the refrigeration system as it is for the air conditioner in your vehicle, as it is for the fridge at home. The cycle is, that's it. Components being used, different of course, but the cycle is the cycle. Next. So I'm going to want to orient you to some of the equipment. You know, we got this thing, this compressor. I talked about a screw compressor. The screw compressor is a rotary device that has, well, they look like screws, two counter-opposing rotating members that interlock as they turn, and it kind of looks like a pencil sharpener, if you can imagine that. The gas that comes in at one end, as the lobes turn, block or open and then block the suction port, and so what's trapped in that lobe as the thing continues to turn, it's moving this way just like a conveyor, and as it comes to the end, it's meeting a resistance and the pressure is increased. So you have this everlasting rotation. On screw compressors, they turn fast. Traditionally, it's about 3,500 RPM. A 2-pole electric motor spins at roughly 3,600. But some designs can go up into the 4,000, 5,000 RPM range. Some will go less than, especially today's world where we're using variable frequency drives to change the capacity of the machine by actually changing its rotational displacement. Point is it's always just flowing that way, and it has a certain signature of sound and vibration.
Is it more like an auger or?
Boy, it's like a twin screw auger that you put a granular or ice in, and as the screws turn, you get this motion going forward. Yeah, it's fascinating. So they have components. There's a strainer. There's an inlet check valve. When this machine stops, you don't want the high pressure squirting backwards through the system. Check valves are there to keep that from happening. We have the compressor. There's a motor, the motor connection box. There's an oil filter, an oil pump, a regulator for the pressure of the oil. That's a hydraulic. That's a hydraulic action. And the intent is to have a pressure that's higher than your operating pressure so that the oil can be injected through the injection lines into the bearings and into the body of the compressor. The oil on a screw compressor is how the heat of compression is absorbed from the machine. In the tables where you see a pressure and a corresponding temperature, that's for the conditions where you are a saturated condition. You don't want to be in a saturated condition coming out of a compressor. It has to be hotter. But the point is if you walk up on one of my compressors and you see that I'm discharging at 165 psi-G, and you look at the table and you say, hey, that should only be 80 degrees, but that discharge gas is 140, there must be something terribly wrong. No, that is normal. That's a condition called superheated, and that's where the temperature of the gas is at a temperature that's higher than its saturated condition. You've got subcooled, you got saturated, and you got superheated. The refrigerant is always one of those three, and that's what I expect of you to learn as you become my operator, is what is the condition out there, and is that the right condition? That's where you will eventually be trained up to do. There's a control panel. Today's control panels are really cool because they got Ethernet protocols where you can access them now and remotely. They're great tools, but a lot of facilities are 1980s, 90s pre-IP addressable devices, but still very, very good controls. That coalescing bandway, that's
Sorry.
good. Go ahead. Go on to the next one. Another kind of compressor is what they call a reciprocating compressor. This is like the engine in your car where you've got pistons that slide up and down, and there's a crankshaft that turns that has the connections for the connecting rods on eccentrics, and so as the shaft is turned by the motor, these pistons are going up and down, up and down. So it has a different sound signature and a vibration. But they have things in common, such as the suction stop valve, the discharge stop valves, just like my screw compressor package. Got motor, I have pressure switches. Pressure switches are there to control the limits. If my suction pressure goes lower than I need, the switch will transfer from on to off and turn off the motor. And the pressure in the system will build back up to where it says, okay, give me refrigeration again. That's how I maintain that pressure that I need out there where I'm absorbing heat to keep it uniform. There's oil coolers, there's filters, the pressure switches, and again, the motor and a direct coupled shaft. So this one turns probably about 1,200 RPM. This is a 12-cylinder machine, and that's probably a 200-horse motor, just for sizing. But these are the things you're going to be looking at for me. Pressure gauges. You're going to be reading pressure gauges and recording them for me. And this pressure gauge has two scales. We have the pressure scale, that's the black, and then we have the red temperature scale. the temperature scale and the pressure scale correspond to the physical properties of ammonia when it's saturated. So as you're looking at here, this gauge is pointing to 0 psig, which corresponds to that minus 28 that you're all familiar with in the MSDS. That's when it's saturated. Sir? Yeah, the question is, how do you describe saturated? When a fluid is at a temperature, it has a vapor pressure potential. And when now my refrigeration description here, the classical is you're saturated when the evaporation of molecules leaving the fluid and the return of the molecules come back are in equilibrium. But for refrigeration, here's what it means to me. I've got the liquid, and I've put in enough heat energy where the liquid and the pressure are in agreement to that gauge. As I add more heat energy, I'm going to get a response. And the liquid will now evaporate into a gas. It's at that point that my liquid is ready to evaporate, that I'm saturated, I'm in agreement with my pressure and temperature, and it's ready to evaporate. And the converse of that, in my condenser, my gas temperature and pressure is where that gas is ready to condense into a liquid if I move more heat out of that gas. So to me, in refrigeration terms, that's the saturation point. That's where I can trust what's happening here if I know that I'm saturated. In the system, you have saturation happening at 2 locations. In the evaporator, somewhere in the evaporator, you are absolutely in saturation. And also in the evaporator condenser. Those are the 2 places where you can always know that there's saturation going on, because if you don't have saturation, you're not getting the work done. Other parts of the system, it might be somewhere in between. It could be where the temperature of the refrigerant is higher than the pressure it's showing. That's normal, but that's a hard concept. But it is normal. And there's places where the pressure or the temperature is lower. For example, at the outlet of the pump that goes out to the units, the pressure could be, grab a number, 30 psig, but my system is operating at 15 psig as far as compression. The fluid has the mechanical energy of the work of the pump. That is called subcooled, because our pressure and our vapor pressure are not in agreement. Those are all part of the nuances of industrial refrigeration that we work with in order to get the job done. So, long story short, for refrigeration, the fluid is ready to change state, and the direction of heat energy coming in will be saturated to make gas, and heat energy going out will take from the gas and back into a liquid. So, part of your tools. I'm going to equip you with eyeglasses, and earplugs, maybe a bump hat. I want you to be wearing the right shoes, coveralls for the kind of exposures that you can expect. And in my systems, you're not going to be expecting too much exposures to bad things. But that's the reason I have you out there, is to tell me that, hey, we got some problems here. So what are we looking for? We are looking for you to use your eyes. Does it look right? That's okay. It's perfect. So you're going to be coming to like a control panel here, and using your eyes, you're going to look at the different values of the running system, and you'll record it on the log sheets that I haven't had you pick up yet, but that's okay. There's a lot of information on this log sheet, and I'm not even going to really refer to it, but this is an example that we produced for our Chronicle. Again, it's, the value of the log sheet is this. every day it's being looked at. Might be only once in 24 hours, or might be twice, but as you accumulate these, you have the trending. And then as a qualified person is looking at these trends, you can see what's happening to the life of the system. On this one, this is kind of neat. It has columns for yesterday and now. So what that means is somebody's got to take yesterday's and transpose the information to here, which, as you said, that's nice. The manager might think, can't I just do this electronically, and might figure out a way to. Actually, there's nothing wrong with creating this as an electronic form. Push the button, have the data fields populate how yesterday was, and then you go and fill it out. There's ways to do it. But the point is this is your reference, and it's very necessary. It's simple to do. You don't have to be a rocket scientist to do it, but you have to. I have to teach you to understand what the values mean, and we'll cover the things of, if it's above this, hey, call me on the radio now, or whatever. Also, there are enunciators of other types. Here's a nice old 1987 panel that's still in service, and it's a very simple panel: switches and lights, and the lights tell you, we've got an oil pressure failure, we've got a high pressure, whatever. Runtime meters. It's all information to be used. Next. So we have things. I'm going to have you look at liquid levels. Liquid levels are really important. I have vessels. When I say I, just don't mean me personally, but just me industry, okay? Vessels. This vessel is a vessel that works at 0 psig. And I have gas that's coming down into it, and the purpose of it is to protect my compressor should liquid return from the evaporator. Things happen that will cause liquid to return, and if I don't have a place to settle it out, that liquid will carry on into the compressor, and that's unhappy. Some compressors have more tolerance for liquid carryover than others. So we invest in a vessel called a suction accumulator. That's the appropriate term for this device. You go out in the field, you might hear a slop tank or a knockout drum. Well, they're talking about the function, but it's a suction accumulator. Liquid levels, what you're going to be looking at is you're going to be looking at these bullseye glasses that when there is a liquid level there, the appearance of it is darker than one that you compare to where the liquid is not. You can't tell too well in this particular illustration, but that's what you're reading for me. Sight glass 1, 2, 3, 4, and there are level switches. Also, there's other vessels. That one I just showed you is vertical in nature. We have vessels that are horizontal, but we have columns. They call them the float columns, and these things that are nicely insulated here are the float switches. The float switches will tell us what the apparent level is in the major vessel because of the equalizing effect of the liquid seeking its own level. And in this float switch, there's actually a float, kind of like the one in your toilet, so to speak, that is riding buoyantly on the level, and that float is driving a rod up inside of the sleeve that there's a magnetic coupling on the end of a lever, and when that rod comes up close enough, it couples over, and that works a micro switch. It's very simple. This device changed the industry in the 60s. Because in the 60s, when you were operating an industrial refrigeration plant, it was manned 24/7. There were no devices that reliably would keep the right level in the tank. So men had to watch the levels in the tanks, and they had to manually throttle valves to limit what's going out into the cold box and coming back. They would read, when I say read, they would observe the piping coming back and the frost line that's on the pipe, and if it got too close to the compressor, they knew they had to pinch it off. That was that was every day. That's how I mean, it was like the engineer on the steam locomotive. If he went to sleep, you ran through town at 80 miles an hour. That's how it was. This was like one of the turning points in the industry as far as an apparatus, because now you can maintain a level without having 24/7 eyes on it. So that was a game changer in the industry when that was developed. We have levels on other tanks. This is a high pressure receiver that is in that building that I showed you. And it also has level eyes and a switch. The purpose of that switch is to keep a minimum level in the tank. On that first vessel I showed you, I had a level switch there, and that was to protect the compressor. If I get that much in there, I don't want my compressor running anymore. It's going to be dangerous. The previous slide, that's a vessel where I want to maintain a level. Point is the same gadget provides different functions. Float switch. Oh, there's our king valve, right there at the bottom of this tank. Now the king valve is that's nomenclature that everybody knows exists, and by function it's basically defined as the primary line that will take liquid from the high pressure receiver to dispense out to the system. Up here is an electric king valve. This line comes here, goes around the corner, goes up like that, and out to the system. So many times you know that the first to change bearings on it. Long story short, he was killed. Did not do an appropriate pump out. The responding engine company, the state police, the Department of Homeland Security all responded to this particular incident. It was only 106 degrees in South Carolina, but they had closed every valve they possibly could. The contractor took him more than 2 hours to go through the gauntlet of security checkup and proving his credentials. He finally said, look, I am the executive vice president of the Refrigerating Engineers and Technicians Association. My company maintains this plant. Let us help you. He finally got through. Then he saw what they had done, and he had to take action to relieve that pressure that was building. Thank God they didn't have the secondary release because of the response tactics of a little bit of knowledge is dangerous. Knowledge applied is power. They didn't know. They just followed we got to close these things because it's coming out. And they averted a real problem because, God, I'd hate to have seen that news article. Department of Homeland Security wiped out by ammonia plant. Oh, geez. So, you're forewarned. Yes?
I'd just like to add to that too. The emergency action plan is very critical because for LA County, when we work with hazmat team, it's very critical to have pictures to tell them if you have solenoid, don't touch this, because from our experience when we get into the investigation, the contractor takes a lot of time to get to the facility. And one time the hazmat doesn't know their facilities, emergency action plan is really critical, so if you have clients, it's good to have that. You always have like pictures,
Mhm.
because client guys are, they're really visual, this is what they're looking for. If there's an incident, there's a situation, this is how you handle it. So those are.
Right. And the point she's making is the pre-planning. The pre-planning with the illustration. Aunt Bee and Andy Griffith taught you a lot in that 6 minutes. And you're going to remember that. The pre-plan, the photographs, this is what it looks like under the normal conditions, will expedite an appropriate response. So encourage your customers to consider that as you're reviewing their emergency action plans. Because some of them might just say, well, our emergency response plan is we're non-responding, so we're going to ring the bell and run. Well, no, they have a larger responsibility. They should have an emergency action plan. In the SARA Title III, it's stated in there someplace. I'm going back many years, but the point is the facility is expected to be able to respond to an upset in their plant. Now, when you consider the 1910-120Q classical response versus being able to respond to a situation, there is a differential. It's our responsibility as the facility to define what we'll do within the limits of our training and resources, and that's exactly what you pointed out, is the pre-plan, the photograph, and the conveying of the message when you don't have a lot of time to really take it in. Thank you.
For us, I know for our county, our county the last 2 years have been struggling to have some type of plan so they could respond.
Uh-huh.
So for us, myself, this company, we're already gearing to set up our own hazmat team.
Mm-hmm.
And right now, because of the, I guess, the legalities and the politics within the San Jose County, what they're trying to do is come up with a plan. So we're coming up with an agreement, all of us 60-something companies, some type of agreement with it, that they will work with us on behalf of those emergencies.
Lucy. Ah, good to see you. Lucy's talking about a mutual aid agreement amongst the industrial community there where her plant is. And yes, it's always a dicey situation when you're considering the classic 1910-120Q, because as you take your training, you doing everything from hazard recognition, what is it, the proper whatever, and the time that it takes to do it. And then on the other side, you got the cowboys running in with the bandana over their face to close the valve. And somewhere in between, you're finding the practical solution with community support. Let us know how that works out for you.
Trying to do a collaboration between the new hazmat team and my hazmat team.
Fantastic.
Because it's always going to work.
That's very encouraging.
Yeah, so we're doing that right now, and we're in the talks with the trainer for the whole hazmat team, and Veronia, which is my field inspector, we're geared to, it's going to be 2013, hopefully we'll get that.
It warms my heart because we're talking about a collaborative activity between agencies and industry in a certain community. And isn't that what it's all about?
And all our guys, we have 8 guys that are just going through book 1 and
Uh-huh.
book 1 and book 2.
Great.
And then we've got one guy already in Cairo. We're going to get 41 Cairo. We're going to area up to have between 8 to 12 of the hazmat team within our own.
Oh, super. The struggling point of all that, we can put together the people that can do the job. It's the legal guys. It's the legal guys and the insurance. Working that solution out is the struggle. But I'm glad you're doing it. Thank you.
One more question.
Yes.
We got 5 minutes, Don.
5 minutes?
Yeah,
I'm sorry.
pretty much. 6.
Has anybody looked at you touched on it earlier, the difference between emergency and non-emergency response. Just because you've got a valve that's listed, that doesn't mean that you go into emergency response mode and leave enough place to get at it outside.
Right. What Carter's talking about is you have relief valve you were mentioning, or a valve that's lifted. That comes down to your sizing up and your preparedness. What can we do if this relief valve lifts? The decision is to the people on site at the time, and as you look at the what's available, again, what are my resources? It's not that every odor investigation is not an emergency. So it does come back down to us being ready.
And figuring out pre-planning a legal way to deal with it.
To satisfy all those conditions, yeah. Literally 5 minutes?
Yep.
Okay, move ahead. Frost and ice patterns. Those are clues for you on your evaporators. Click. Move ahead. Yeah.
Oh, yeah.
Here's a good example of what you don't want to see. This is a lot of frost and ice on this evaporator. The real hazard here is when it warms up and falls off and hits you on the head. The cause of this is warm air entering in that cold space and frosting out on every cold surface that's available. That's a great example of a bad example. Another kind of problem that we can see is an ice berm building up at the bottom of the evaporator. This happens to be a picture of a vertical-faced evaporator, and it had this big lob over of ice at the bottom. The reason for it is there was oil built up in this thing, and so the defrosting heat could not get to the surface to melt the ice in the time available, and it builds this thing up. The scary part was the idiot forklift operator that was using the forklift like an ice pick because he thought it would be cool. And when our manager saw that happening, we had a teachable moment. in your
Well, we had that. Yeah, okay.
oil pots. Oil pots are very nice to have because it gives you a way to manage. What you're looking at here is where there isn't ammonia, there is not frost, there's something else. Here it's the oil, so it tells you how much oil is here so that it can be drained. And this photograph was, here we got the valve. We don't have that self-closing ball valve downstream. It's because the utility here, the utility people carried the ball valve with them, and they would put it on, then drain the oil, and move on to the next. You notice it does have the plug. Next. So then, okay, what's the next tool you have? You got your nose. Now, I will give you a personal monitor, 0 to 400, and the reason for it is not that you're going to know that you have the ammonia before it does. Your nose will do that for you, but it'll tell you how bad it is. Sometimes we have to work in an environment where it is kind of stinky, and we want to make sure that if we're wearing our air purifying respirators and our level D coveralls to deal with a seal leak or packing on a valve, that we are working in an environment that our respirator is rated for. And that's one of the purposes of that personal monitor. That's something I'll give you. I don't read it in code that I have to supply that to everybody, but it's my elective to provide that. The nose, though, is a great example. We saw that picture.
Yep.
The earplugs, but I tell you what, your ears, as my rounds person, are just critical, because you can hear the change of pitch when a bearing goes into distress or a vibration or whatever. So hearing, very, very good. Next. When it gets quiet in an engine room, that's kind of a high suspense moment, because, well, you saw it in the film. the freezer quit, but we all believe that the freezer should keep running. In an engine room, if it gets quiet, you know, something could be amiss, and it could be something as simple as the ammonia detectors have picked up enough of an odor that says shut off, or might have tripped a breaker or whatever. But again, back to the hearing, is this normal? Is this right? Next. So that takes us to our second one, gauges. I'm going to teach you how to read those gauges and what it means, the highs and the lows, and when to believe that the corresponding temperature and pressure, that is what you should see, and when you shouldn't. Also, you know, today we've got electronic controls that give us digital display readouts. And some facilities you can read what's going on anywhere in the world because they're connected to the internet. Well, you have these transducers that actually take that mechanical pressure and convert it into a signal, but you need to validate that with a gauge nearby so that if they're in agreement, it's good. If one starts to drift and you got disagreement, now you've got a reason to go in and calibrate or revalidate which one is right and realign it. So gauges and transducers together is a good thing to have. Thermometers, we're all about maintaining a temperature, and the thermometers tell you the information. Are the conditions right in the cold box? Is my refrigerant temperature right? And level indicators. Click. Send back to the, back to these, that's good. That's good. Level indicators, you know, you're going to record for me where is our apparent level in this unit. We'll be looking it over time. You know, three level switches here. This one will shut off the machine if it gets too high. This one says, I want to have at least this much. This one here is to protect the pump. If it goes too low, I'll cavitate the pump. I'll have a seal problem. So when it gets to there. So again, same part number, different functions, but all have to do with the needs of the system. But there's other levels that I'm concerned about too. How about my water treatment? How much is in here? And we're looking for rate of use. If suddenly we gulp down a quarter of this barrel overnight, I might have an issue with my evaporative condenser in a very short time, especially if I'm using an acidic product here. So watching that rate of consumption is an important part of our job. There's other levels to be concerned about too. This happens to be an ammonia diffusion tank that's hooked up to the relief valves. And you know, if the level climbs in here, there's got to be a reason. The easiest thing to find out is if we added ammonia is to take a water sample and get the pH of it. But you want to make sure that you always have at least the right amount. My rule of thumb is on my vertical tanks, it's 5/8 full of water. That's the standing quantity. And how much is there is a calculation of size of your relief valves, etc. As the refrigerant goes into that water, you're adding mass to the water. It's got to go somewhere, and it's going to result as more fluid in the tank. So you got to have a place to swell into. Also, it's going to get pretty warm. It can get well over 100, 120 degrees with that heated reaction as ammonia dissolves into water. There's a condensation going on. There's an energy exchange. So the water needs to swell up and occupy a space too. So when I ran the numbers when we started building these for systems, 5/8 of it is for the standing water, and the 3/8 is the headspace to absorb what I expect it to receive and still keep it from spilling over. That's what we do. Also, we put an inverted P-trap here with a vacuum breaker there. I've measured 25 inches of vacuum in a line that's delivering from a relief valve to a water tank. The absorption of ammonia to water is frightening. It is so, it happens so fast that this line actually went into a vacuum. And if it's going into a vacuum, it's going to reverse flow and push water back to my relief valves. And so the vacuum breaker there is there to prevent that from happening. Temperatures and gauges. One of the things that we're always concerned about is what is our head pressure, and is our head pressure what it should be? Is there another gas, a non-condensable gas in my system that is causing the pressure from the discharge of the compressors to be higher than it should be? And so we're looking at, are we in agreement with our temperature of our condensate coming out of the condenser and the condensing pressure? Not the head pressure in the engine room, but the pressure out there at the condenser, because we could have pressure drop between compressor and condenser. So we're looking for agreement here with pressure and temperature, and when it's not right, we have to decide when is the time to purge. Let's see, the other point was counters. Next slide. Alarm indicators, next. Counters. Counters, such as this gadget here. This is that suction trap, suction accumulator. They're using the slang, I don't want to. Suction accumulator, and its purpose is to protect the compressors that's downstream from the evaporators that are upstream. And there's a vessel here that this drains into. It's got a level switch, and as this gets full enough, switches actuate and it pumps the refrigerant back out from here back to the receiver. If that is happening too often, that tells me, hey, we got a problem somewhere out there. We need to, this is not supposed to be a recirculator. It's an occasional functioning thing. So that tells me as the plant engineer, it's time to go look to see what is causing an overfeed, such as you go to your PHA. What if the valve sticks open that is feeding the unit? What are the consequences? So that's how you use the benefit of the PHA to resolve a problem, or to even make a person aware of the problem. So there's other issues too with the physical condition of the equipment, such as, you know, when you look at this at first, it might give you a strong concern. Don't be. This is okay. The structure is sound. The protection of the piping and the strawberries here, and this is not a high-speed traffic area of the facility. The evaporative condenser. You know, what is the condition there? Are the bearings okay? Or the fan blade mounts all right? The housing, the volute, you know, are we good? The motor mounting, you're looking for these things as my rounds person. Next. And you're also going to take just a look down the roof, and you're going to be looking for, well, is there steam coming off where it shouldn't? That steam might be an indicator of little ammonia leaking out onto the roof and whatever. So you're going to occasionally look at that for me too. And you can also enjoy the view down the Salinas Valley. We thank you.
Thank you.
I do want, if you give me 3 minutes, Lee, can you bring up that picture of that vessel?
Which one?
Okay. Here's a good example of a bad example. You as the regulator walk up and you see this. What's your first concern? Cool. This one or this one? Oh, that one. Yeah. What else? If you can go to zoom, and if that was 250 or 200, go to like 160. Okay, so we're looking at this. This is not in any of your jurisdictions, by the way. Truly, it isn't. It is a suction accumulator, thank you. And so we have the frost line, we call those Casper tracks. See, because Casper, the friendly ghost, can go through walls and such. But when he goes through, if the air is carrying moisture, the moisture doesn't go through with him and it freezes out. That's a great operator tool. Well, we see the apparent level in this vessel. Now, I know you're already concerned, okay, what about this bucket? And I bet you're concerned about, well, apparently they're dumping that oil into here, and clearly it does not have an accumulation sticker, right? Oil waste and all that, and there's no secondary containment. But we've got here, you can see the level switch, and there is a red light. But do you see Casper tracks? No. If I got Casper here, but I don't have him there, I must have something else there, like a lot of oil. So the red light's not lit, but the apparent level is higher than the safety. And those are part of the clues that you, as my rounds person, will be trained on to be looking for. On this one, yes, we got this rust-colored paint. We don't know about the seismic, but this is not in California. Literally, it is not. But it was such a neat picture, I had to stop and take it because it's a teachable moment. Yeah, now, they got a 55-gallon drum of oil there. They've been draining the oil. The oil is hanging on a 1/4-inch pipe nipple that's got a gauge valve, and that's one place where they've been draining the oil out of this float column. And they're leaving it there. So, 5 gallons of oil weighs, 50 pounds? Hanging on a 1/4-inch pipe nipple, for God's sake. A good example of a bad way to operate. You can even go into the technical side. You got a globe valve here that the flow through a globe valve kind of has to take a course like that. And so you end up with a dam the outlet is holding back what's on the inlet side. But if they had just rolled that thing over so that the path was horizontal through, things like oil going to this is what you're counting on for your instrumentation. Now, please don't go out and tell everybody you got to roll your valves over. But when they're installed, comment, hey, that one is turned to the side. I just learned that that's a good idea. Good for you. But here's a great example of a way you don't want to operate. With ammonia, the pressure and the temperature of ammonia at 32 degrees is roughly 49 psig. So if we've got ice forming here, you could assume, hey, the pressure in this system is less than 49. You don't know how much less, but it is at least low, relatively speaking. I see relief valves, but I don't see carry-away piping. There's a lot here to final exam. I appreciate your tolerance and patience with us today. I hope you found it to be worthwhile. We do have a couple other versions of the Rita Breeze we want you to take. Agencies at rita.com. Engage with us as industry. Come to the Ammonia Safety Days. Central Valley, the Bakersfield area Safety Days sometime in late March, I believe. March 7th. February 28th, over on the other side of the Colorado River, Yuma area, Ammonia Safety Day, 9th annual. May 26th, I believe, and Salinas, 20th annual. Fantastic. Fantastic. And the reason for them...
LAIE.
The reason for them... Thank you, Rebecca. The reason for those safety days is to engage us all together to talk about a common goal. Safer community, safety, and keeping industry in business in your jurisdiction so that you have a job. And together that can be done, and these safety days are a great vehicle for making that happen. Again, Lee and I, we thank you so much. So next year you want an 8-hour refresher going through book 1?